Light is the fastest thing in the universe, yet black holes bend the very fabric of space and time, creating regions where the known laws of physics seem to collapse. Could light in these extreme environments lose its speed? Tonight, we explore the mysterious nature of light, the forces inside black holes, and whether light could slow down at the edge of the universe's most enigmatic objects. Imagine standing at the edge of the cosmos, where darkness meets light in the most dramatic way possible. Here, in the depths of space, massive objects called black holes lurk like cosmic monsters, devouring everything that comes too close. They are invisible hunters, revealing themselves only through the brilliant glow of matter spiraling into their deadly embrace. For centuries, humans have looked up at the night sky and wondered about the nature of light. We see it streaming from distant stars, carrying messages from worlds billions of miles away. Light connects us to the universe, allowing us to witness the birth and death of celestial bodies across unimaginable distances. But what happens when this fundamental force of nature encounters something so powerful that it can trap light itself? Black holes represent the ultimate extreme in our universe. They are places where gravity becomes so intense that it creates a point of no return, a boundary called the event horizon. Beyond this invisible line, nothing can escape, not even the fastest thing we know, light itself. Yet this raises a profound question that has puzzled scientists for decades. If light cannot escape from inside a black hole, what exactly happens to it in there? The story of light begins with its incredible speed. In the vacuum of space, light travels at 299,792,458 meters per second. This speed is not just fast, it is the ultimate speed limit of the universe. Nothing can travel faster than light, and this fundamental fact shapes everything we understand about space, time, and reality itself. But here is where the mystery deepens. Black holes do not just capture light, they bend and warp the very fabric of space and time around them. This warping is so extreme that it changes the rules of physics themselves. Time slows down, space stretches, and the normal behavior of matter and energy becomes something entirely alien to our everyday experience. Picture a cosmic whirlpool, but instead of water, it is made of twisted space and time. As objects fall toward a black hole, they experience forces that would tear apart planets and stars. The gravity becomes so strong that it pulls on different parts of an object with different intensities, stretching it like taffy in a process scientists call spaghettification. Yet, light, being massless, should theoretically be immune to some of these effects. Light does not have weight in the traditional sense, so it should not be pulled down by gravity the way a falling rock would be. Instead, light follows the curves and bends that massive objects create in space-time. It is like a marble rolling along a curved surface, following the path that has been laid out for it by the warping of reality itself. This leads us to tonight's central question. In the extreme environment inside a black hole, where space and time become so distorted that our normal understanding breaks down, could light itself be forced to slow down? Could the fastest thing in the universe find itself trapped in a cosmic prison where even its fundamental nature is changed? The answer to this question touches on some of the deepest mysteries in physics. It involves the strange relationship between gravity and light, the nature of space and time themselves, and the limits of what we can know about the universe. As we embark on this journey into the heart of cosmic darkness, we will explore ideas that challenge everything we think we know about reality. Some of the greatest minds in history have grappled with these questions. Albert Einstein, whose theories first predicted the existence of black holes, showed us that space and time are not fixed stages on which cosmic events play out. Instead, they are dynamic, flexible, and can be bent, stretched, and compressed by the presence of matter and energy. Stephen Hawking took these ideas even further, showing us that black holes are not just cosmic vacuum cleaners that suck up everything around them. They are complex objects with their own temperature, their own radiation, and their own strange quantum properties that blur the line between matter and energy, between existence and nothingness. Tonight, we stand at the threshold of these cosmic mysteries, ready to peer into the darkness and ask questions that may not have easy answers. We will explore the possibility that light, the constant companion that illuminates our world and connects us to the stars, might behave in ways we never imagined when trapped in the most extreme environments the universe has to offer. As we begin this journey, remember that we are not just talking about distant objects in space. We are exploring the fundamental nature of reality itself, the rules that govern everything from the smallest particles to the largest structures in the cosmos. The story of light inside black holes is ultimately the story of how the universe works at its most extreme limits. So settle in and prepare to have your understanding of light, space, and time gently challenged and expanded. We are about to explore one of the most profound questions in modern physics, and along the way, we might discover that the universe is even stranger and more wonderful than we ever dared to imagine. To understand what might happen to light inside a black hole, we must first appreciate the extraordinary nature of light itself in our everyday universe. Light is not just fast. It is the fundamental speed limit that governs all of reality. Every photon that reaches your eyes from a distant star has traveled at exactly the same speed for millions or billions of years, never slowing down, never speeding up, maintaining its perfect cosmic velocity through the vast emptiness of space. The speed of light in a vacuum is 299,792,458 meters per second. This number is not arbitrary. It is built into the very fabric of the universe. Scientists have measured this speed with incredible precision, and no matter where they look or what they measure, light always travels at exactly this speed when moving through empty space. This consistency is remarkable when you think about it. A photon leaving the surface of the sun takes about 8 minutes and 20 seconds to reach Earth. During this journey, it maintains its speed perfectly, never wavering, never slowing down due to the gravitational pull of planets or the solar wind. It arrives at your eye with the same energy and velocity it had when it left the sun's surface 93 million miles away. But why is light so special? Why does it hold this unique position as the ultimate speed limit in the universe? The answer lies in the fundamental structure of space and time themselves. Light does not just move through space and time, it actually defines the relationship between space and time. This is the profound insight that Albert Einstein gave us in 1905 with his special theory of relativity. Einstein realized that space and time are not separate things, but are woven together into a single fabric called space-time. The speed of light is like the exchange rate between space and time, determining how much space equals how much time in the cosmic economy. When you move very fast, approaching the speed of light, time slows down for you relative to someone standing still. This is not science fiction. It is a measured reality that affects everything from GPS satellites to particle accelerators. The reason nothing can travel faster than light is that doing so would require infinite energy. As objects with mass approach the speed of light, they become heavier and heavier, requiring more and more energy to accelerate them further. At the speed of light itself, the energy requirement becomes infinite, making it impossible for anything with mass to reach this ultimate velocity. Light achieves this speed effortlessly because photons, the particles of light, have no mass at all. They are pure energy, pure information, moving through space at the only speed they can possibly travel. In fact, from the perspective of a photon, no time passes at all during its journey. A photon that left a star billions of years ago experiences no passage of time from its own reference frame. It exists in an eternal now, experiencing its emission and absorption as a single instantaneous event. This massless nature of light gives it other remarkable properties. Light cannot slow down or speed up in empty space. It can only maintain its constant velocity. When light appears to slow down, such as when passing through water or glass, it is actually being absorbed and re-emitted by atoms in the material. The light itself still travels at the speed of light between these interactions, but the constant absorption and re-emission creates an effective slower speed through the medium. The speed of light also serves as a cosmic speed limit for information itself. Nothing can carry information faster than light, which means that cause and effect relationships in the universe are governed by light speed. If something happens on a distant star, we cannot know about it until light from that event reaches us. This creates what physicists call light cones, regions of space-time that define what events can influence each other. In our everyday world, light seems instantaneous. When you flip a light switch, the room appears to illuminate immediately. But this is only because the distances involved are so small compared to light's incredible speed. Even in a large room, light takes only a few billionths of a second to travel from the bulb to the walls. Our brains cannot process such tiny time intervals, so the lighting appears instant. On cosmic scales, however, the finite speed of light becomes dramatically apparent. The nearest star to our Sun, Proxima Centauri, is about 4 1/3 light years away. This means that the light we see from this star tonight actually left the star over 4 years ago. We are literally seeing into the past every time we look at the night sky. The further away an object is, the further back in time we are seeing it. This creates a beautiful consequence for astronomy. Large telescopes are actually time machines, allowing us to observe the universe as it was billions of years ago by capturing light that has been traveling toward us for billions of years. The most distant galaxies we can see show us what the universe looked like when it was young, when the first stars were forming and the cosmic web of matter was just beginning to take shape. The speed of light also plays a crucial role in the structure of atoms themselves. Electrons orbiting atomic nuclei are governed by the same relativistic effects that govern cosmic phenomena. The fine structure constant, which determines the strength of electromagnetic interactions, is directly related to the speed of light. This means that the speed of light influences everything from the colors of the elements to the stability of matter itself. In particle accelerators, scientists routinely accelerate particles to speeds very close to the speed of light. As these particles approach light speed, they become more and more massive, exactly as Einstein predicted. The energy required to push them faster grows exponentially, confirming that the speed of light is indeed an unbreachable barrier for objects with mass. Yet light itself effortlessly cruises at this ultimate speed, carrying energy and information across vast distances without ever tiring or slowing down. A single photon can travel for billions of years through nearly empty space, maintaining its energy and direction across distances that dwarf human comprehension. This remarkable consistency makes light our most reliable messenger from the distant universe. The implications of light's constant speed extend far beyond what we might initially imagine. Consider the simple act of looking at your reflection in a mirror. The light bouncing off your face travels to the mirror and back to your eyes at the speed of light. Even though this happens so quickly that it seems instantaneous, there is actually a tiny delay. You are seeing yourself as you appeared a few billionths of a second ago. This may seem insignificant, but it illustrates a profound truth about the universe. There is no such thing as true simultaneity across space. This leads to one of the most mind-bending consequences of light's finite speed. Events that appear simultaneous to one observer may not be simultaneous to another observer moving at a different speed. This relativity of simultaneity means that the universe has no universal now. Instead, each observer carries their own version of the present moment, defined by their motion through space-time. The speed of light also determines the ultimate fate of the universe itself. As the universe expands, light from distant galaxies becomes stretched and reddened, a phenomenon called redshift. This stretching of light waves tells us not only that the universe is expanding, but that this expansion is actually accelerating. The most distant light we can detect comes from the cosmic microwave background, the afterglow of the Big Bang itself, which has been traveling toward us for nearly 14 billion years. In the realm of quantum mechanics, light reveals even more mysterious properties. Individual photons can exist in multiple states simultaneously, a phenomenon called superposition. They can be entangled with other photons, creating instantaneous correlations across vast distances that Einstein famously called spooky action at a distance. These quantum properties of light have led to revolutionary technologies like quantum computers and quantum cryptography. The measurement of light speed has itself been a journey of discovery spanning centuries. In 1676, the Danish astronomer Ole Rømer made the first successful measurement of light speed by observing the moons of Jupiter. He noticed that the timing of eclipses varied depending on Earth's position in its orbit, and correctly deduced that this was due to the finite speed of light. His measurement was remarkably close to the modern value, considering the crude instruments available at the time. Later, in 1849, Hippolyte Fizeau conducted the first terrestrial measurement of light speed using a rotating gear wheel. Light passed through the gaps between gear teeth, traveled to a distant mirror, and returned. By adjusting the rotation speed of the gear, Fizeau could measure how fast light traveled over a known distance. This experiment brought the measurement of light speed down from astronomical scales to laboratory scales, making it accessible to direct experimentation. The precision of modern light speed measurements is truly extraordinary. Scientists can now measure the speed of light to within a few parts per billion using laser interferometry and atomic clocks. This precision has practical applications beyond pure science. The definition of the meter itself is now based on the speed of light. Defined as the distance light travels in 1,299,792,458th of a second. Light's role in defining space and time becomes even more apparent when we consider GPS satellites. These satellites orbit Earth at high speeds and experience weaker gravity than we do on the surface. Both effects cause time to run differently for the satellites compared to ground-based clocks. If engineers did not account for these relativistic effects, GPS systems would accumulate errors of several miles per day. The fact that GPS works so accurately is a daily confirmation that Einstein's theories about space, time, and the speed of light are correct. The energy carried by light is directly related to its frequency through Planck's constant. Higher frequency light, such as ultraviolet or X-rays, carries more energy per photon than lower frequency light like radio waves. This relationship, discovered by Max Planck in 1900, launched the quantum revolution and helped us understand that light has both wave and particle properties. Sometimes light behaves like a wave, spreading out and interfering with itself. Other times it behaves like a stream of particles, transferring energy in discrete packets. This wave-particle duality of light challenged scientists for decades. How could something be both a wave and a particle at the same time? The answer came with the development of quantum mechanics, which showed that this apparent contradiction is actually a fundamental feature of reality at the quantum scale. Light is neither purely a wave nor purely a particle, but something that incorporates aspects of both, depending on how we choose to observe it. In the context of stellar astronomy, Light serves as our primary tool for understanding the cosmos. When starlight passes through stellar atmospheres, different elements absorb specific wavelengths, creating dark lines in the spectrum. These absorption lines are like fingerprints, allowing astronomers to determine the chemical composition, temperature, density, and motion of distant stars. Through spectroscopy, we have learned that the same elements we find on Earth exist throughout the universe, unified by the universal language of light. The Doppler effect, which shifts the frequency of light from moving sources, has revolutionized our understanding of cosmic motion. Light from objects moving toward us is shifted toward higher frequencies, appearing bluer, while light from objects moving away is shifted toward lower frequencies, appearing redder. This effect allowed Edwin Hubble to discover that the universe is expanding, fundamentally changing our understanding of cosmology. Even more remarkably, light can be gravitationally lensed by massive objects, bending its path through space. This effect, predicted by Einstein's general relativity, allows astronomers to use galaxies and galaxy clusters as natural telescopes, magnifying and distorting the light from even more distant objects behind them. Gravitational lensing has become a powerful tool for studying dark matter, dark energy, and the large-scale structure of the universe. The polarization of light provides yet another avenue for cosmic exploration. Light waves can vibrate in different orientations, and this polarization can be affected by magnetic fields, dust, and other cosmic phenomena. By studying polarized light from stars and galaxies, astronomers can map magnetic fields throughout the universe and understand the role of magnetism in cosmic evolution. As we contemplate these remarkable properties of light, we begin to appreciate just how fundamental it is to our understanding of reality. Light is not just something that helps us see, it is the very fabric that connects cause and effect across the universe. It carries information about the past, defines the flow of time, and sets the ultimate limits on what is possible in our cosmic neighborhood. But what happens when this perfectly consistent, utterly reliable cosmic constant encounters something as extreme as a black hole? Can the fundamental nature of light itself be altered by the most powerful gravitational fields in the universe? Can the speed that defines the very structure of space-time be changed in regions where space-time itself becomes infinitely curved? As we prepare to explore these questions, we carry with us an appreciation for just how extraordinary and fundamental the speed of light truly is in shaping the reality we experience every day. Light travels through the universe at a constant speed, defining our experience of time and space. But what happens when the very nature of space and time itself is bent, stretched, and compressed? Deep in the cosmic darkness, there exist objects so strange and powerful that they challenge our very understanding of reality. Black holes are regions of space where gravity has become so intense that it creates a point of no return, a boundary beyond which nothing, not even light itself, can escape. To truly comprehend what might happen to light inside these cosmic monsters, we must first understand what black holes are and how they come to exist in our universe. Imagine trying to throw a ball so hard that it never falls back down to Earth. You would need to throw it at a speed of about 11 kilometers per second, fast enough to overcome Earth's gravitational pull completely. This is called the escape velocity. Every celestial body has an escape velocity that depends on its mass and size. The more massive an object is, and the smaller it is, the higher its escape velocity becomes. Now imagine an object so massive and so compact that its escape velocity exceeds the speed of light itself. Since nothing can travel faster than light, nothing can escape from such an object once it gets too close. This is the fundamental concept behind a black hole. It is not that black holes suck things in like cosmic vacuum cleaners, but rather that they create a region of space where the escape velocity exceeds the ultimate speed limit of the universe. The journey toward understanding black holes began in 1783 with a brilliant English clergyman named John Michell. He imagined what he called dark stars, objects so massive that light could not escape from them. This was long before Einstein's theories, so Michell was thinking in terms of Newton's physics, but his insight was remarkably prescient. He realized that there could exist objects in the universe that would be invisible to us because their gravity was too strong for light to escape. The modern understanding of black holes emerged from Einstein's general theory of relativity, published in 1915. Einstein showed that massive objects actually warp the fabric of space and time around them. This warping is what we experience as gravity. The more massive an object is, the more it warps space-time, and the stronger its gravitational effects become. Just months after Einstein published his theory, a German physicist named Karl Schwarzschild found a mathematical solution that described the space-time around a spherically symmetric massive object. Schwarzschild was serving as a soldier on the Russian front during World War I when he made this calculation. Tragically, he died of an autoimmune disease just months later, but his solution became the foundation for our understanding of black holes. The Schwarzschild solution revealed something startling. It predicted that if enough mass were concentrated into a small enough region, space-time would become so severely warped that it would form what we now call an event horizon. This is an invisible boundary around the central mass where the escape velocity equals the speed of light. Anything that crosses this boundary can never return to the outside universe. But how do black holes actually form in nature? The most common way is through the death of massive stars. Throughout their lives, stars maintain a delicate balance. The outward pressure from nuclear fusion in their cores balances the inward pull of their own gravity. This cosmic tug of war can continue for millions or billions of years, depending on the star's mass. However, even the most massive stars eventually run out of nuclear fuel. When a star more than about 25 times the mass of our Sun exhausts its fuel, the nuclear fires that have been holding it up suddenly go out. Without this outward pressure, the star's enormous mass begins to collapse under its own gravity. This collapse happens incredibly quickly, in just a fraction of a second. The core of the dying star collapses so rapidly and with such force that not even the strong nuclear force, which holds atomic nuclei together, can stop it. Protons and electrons are crushed together to form neutrons, and then even the neutrons are overwhelmed by the incredible gravitational pressure. The core collapses beyond the point where any known force can halt its inward rush. As the core collapses, it becomes smaller and denser, warping space-time more and more severely around it. When the core shrinks to a critical size called the Schwarzschild radius, the curvature of space-time becomes so extreme that an event horizon forms. At this moment, a black hole is born. The collapsing matter disappears behind the event horizon, leaving only its gravitational influence on the surrounding space. The outer layers of the dying star, meanwhile, rebound from the collapsed core in a spectacular explosion called a supernova. This explosion can briefly outshine an entire galaxy, scattering heavy elements forged in the star's nuclear furnace throughout the surrounding space. But at the center of this cosmic fireworks display, hidden behind its newly formed event horizon, lies a black hole. Not all black holes form from dying stars. Supermassive black holes, containing millions or billions of times the mass of our Sun, lurk at the centers of most galaxies, including our own Milky Way. How these giants formed is still something of a mystery. They may have grown from smaller seed black holes that formed in the early universe, or they might have formed directly from the collapse of massive gas clouds in the primordial cosmos. There may also be primordial black holes, formed not from stellar collapse, but from extremely dense regions in the early universe that collapsed under their own gravity shortly after the Big Bang. These primordial black holes could have a wide range of masses, from microscopic to stellar-sized. Some scientists speculate that they might even make up part of the mysterious dark matter that appears to dominate our universe. The size of a black hole's event horizon depends directly on its mass. A black hole with the mass of our Sun would have an event horizon about 6 kilometers across. A black hole with 10 times the Sun's mass would have an event horizon about 60 kilometers across. The supermassive black hole at the center of our galaxy, with a mass of about 4 million suns, has an event horizon roughly the size of Mercury's orbit. But here is where black holes become truly strange. Although we call them black holes, the whole part is somewhat misleading. There is no actual hole in space, no tunnel to somewhere else. Instead, there is an object of incredible density sitting at the center, surrounded by severely warped space-time. This central object is called a singularity, a point where our current understanding of physics breaks down completely. At the singularity, matter is thought to be compressed to infinite density and zero volume. This creates what physicists call a curvature singularity in space-time, a place where the equations of general relativity give infinite answers. Most scientists believe that this infinite density is not physically real, but rather indicates that our current theories are incomplete. We need a theory of quantum gravity to truly understand what happens at the center of a black hole. The event horizon itself is not a physical surface that you could touch. It is simply a boundary in space-time, defined by the point where the escape velocity equals the speed of light. From the outside, the event horizon appears to be a dark sphere. But this darkness is not because it is made of any dark material. It appears dark because no light can escape from within it to reach our eyes. Interestingly, if you were to fall toward a black hole, you would not notice anything special when you crossed the event horizon. There would be no wall, no barrier, no sudden change in your immediate surroundings. You would simply continue falling inward, unaware that you had just crossed the point of no return. This is one of the most counterintuitive aspects of black holes. The event horizon is completely imperceptible to someone crossing it, yet it represents the ultimate boundary in the universe. However, an outside observer watching you fall toward the black hole would see something very different. Due to the extreme warping of space-time near the event horizon, time dilation effects would cause your motion to appear to slow down dramatically as you approached. To the outside observer, you would appear to freeze at the event horizon, your image becoming redder and dimmer as time goes on, but never quite disappearing. This is called the frozen star effect. Black holes also exhibit a property called frame dragging. As they rotate, they literally drag space-time around with them, like honey being stirred by a spoon. This means that near a rotating black hole, it becomes impossible to remain stationary relative to distant stars. You would be forced to orbit in the same direction as the black hole's rotation, carried along by the twisted fabric of space-time itself. The region just outside the event horizon of a rotating black hole is called the ergosphere. In this region, space-time is dragged around so severely that anything within it must rotate with the black hole. Surprisingly, it is theoretically possible to extract energy from a rotating black hole by dropping objects into the ergosphere and allowing them to be flung out by the frame dragging effect with more energy than they had going in. Perhaps most remarkably, black holes are not completely black. In 1974, Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation. This Hawking radiation is incredibly faint for stellar mass black holes, but it means that black holes actually evaporate over extremely long periods of time. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate completely, a time so long that it dwarfs the current age of the universe by an unimaginable factor. The existence of black holes was purely theoretical for decades. Astronomers could not directly observe objects that emit no light. Instead, they had to look for indirect evidence, such as stars orbiting invisible companions or high-energy radiation from matter falling into black holes. The first strong candidate for a black hole was discovered in 1971, an X-ray source called Cygnus X1, where a visible star appeared to be orbiting an invisible object too massive to be anything other than a black hole. Today, we have detected thousands of black hole candidates and have even captured images of the event horizons of supermassive black holes using the Event Horizon Telescope. These images show the shadow of the event horizon surrounded by the brilliant glow of superheated matter in the accretion disk, confirming decades of theoretical predictions about these cosmic giants. As we contemplate these remarkable objects, we begin to appreciate just how extreme the conditions near black holes truly are. They represent the ultimate test of our understanding of gravity, space-time, and the fundamental nature of reality. In their vicinity, the familiar rules of physics are pushed to their absolute limits and sometimes beyond. At the heart of a black hole lies a singularity, a point of infinite density. But what happens to light in this extreme environment? Can the rules of the universe still apply? To understand how light might behave differently near a black hole, we must first grasp one of the most profound insights in all of physics. Space and time are not the fixed, unchanging stage upon which cosmic events unfold. Instead, they form a flexible, dynamic fabric that can be stretched, compressed, twisted, and curved by the presence of matter and energy. Near a black hole, this warping becomes so extreme that it fundamentally alters the nature of reality itself. Imagine space-time as a vast rubber sheet stretched tight. When you place a bowling ball in the center of this sheet, it creates a depression, curving the rubber around it. Now, if you roll a marble across the sheet, it will follow the curves created by the bowling ball, appearing to be attracted to it. This is a simplified way to visualize how mass warps space-time and how that warping manifests as the force we call gravity. But this analogy, while helpful, barely captures the true strangeness of what happens near a black hole. The warping of space-time around these cosmic giants is so severe that it creates effects that seem to defy common sense. Time slows down, distances become distorted, and even the direction of time itself can become ambiguous. These are not just theoretical curiosities, but measurable phenomena that have profound implications for anything, including light, that ventures too close to a black hole. The mathematical description of this warping comes from Einstein's field equations, a set of 10 interconnected differential equations that relate the curvature of space-time to the energy and matter within it. For a non-rotating black hole, the solution to these equations is called the Schwarzschild metric, named after Karl Schwarzschild, who derived it in 1916 while serving on the Russian front during World War I. The Schwarzschild metric reveals that as you approach a black hole, the fabric of space-time becomes increasingly distorted. At large distances, the effects are subtle, barely noticeable compared to the normal gravitational effects we experience around planets and stars. But as you get closer to the event horizon, the distortions become more and more dramatic, until they completely dominate the structure of local space-time. One of the most striking effects of this space-time curvature is gravitational time dilation. Time literally runs slower in stronger gravitational fields. This is not just a theoretical prediction, but a measured reality that affects everything from GPS satellites to atomic clocks. Near a black hole, this effect becomes extreme. Time passes more and more slowly as you approach the event horizon, and at the horizon itself, time appears to stop completely from the perspective of a distant observer. To understand this, Imagine you have a twin who decides to take a journey close to a black hole while you remain safely at a distance. As your twin approaches the black hole, you would observe their clocks running slower and slower. Their movements would appear to slow down, their speech would become deeper and more drawn out, and any light they emit would become redder and dimmer. This is not an illusion or a problem with your instruments. Time genuinely runs slower in the stronger gravitational field near the black hole. From your twin's perspective, however, their own clocks would appear to run normally. They would not feel time slowing down. Instead, they would observe your clocks running faster as they move deeper into the black hole's gravitational well. This reciprocal effect illustrates one of the fundamental principles of relativity. There is no absolute reference frame for measuring time. Time is relative, depending on your motion and your position in a gravitational field. The warping of space is equally dramatic. Distances become stretched and compressed in ways that can only be described mathematically. The familiar geometry of flat space, where the shortest distance between 2 points is a straight line, breaks down completely. Near a black hole, space becomes curved, and what appears to be the shortest path between 2 points may actually be a curved trajectory that follows the warped geometry of space-time. This spatial warping has profound effects on the paths that light takes through the region around a black hole. Light always travels along what physicists call geodesics, the straightest possible paths through curved space-time. In flat space, these geodesics are simply straight lines. But in the curved space-time around a black hole, the geodesics become curved, causing light to bend and follow unexpected trajectories. This bending of light paths creates one of the most beautiful and scientifically useful phenomena associated with black holes: gravitational lensing. When light from a distant star or galaxy passes near a black hole, the curved space-time acts like a lens, bending the light rays and focusing them. This can create multiple images of the same distant object, magnify its apparent brightness, or distort its shape into arcs and rings. Gravitational lensing has become a powerful tool for astronomers. By observing how light from background objects is distorted by intervening black holes or other massive objects, scientists can map the distribution of matter in the universe, including the mysterious dark matter that makes up most of the mass in galaxies and galaxy clusters. The very warping of space-time that makes black holes so exotic also provides us with a way to study the invisible components of our universe. The degree of space-time curvature around a black hole is described by something called the Riemann curvature tensor, a mathematical object that captures all the information about how space-time is bent and twisted in any given region. Near the event horizon of a black hole, this curvature becomes enormous, approaching infinity at the central singularity. This extreme curvature is what creates the exotic effects we observe around black holes. One particularly fascinating aspect of this curvature is that it affects different directions differently. The warping of space-time is not uniform, but varies depending on which direction you are looking. This creates what physicists call tidal effects, similar to the way the moon creates tides on Earth, by pulling more strongly on the side of Earth facing the moon than on the side facing away. Near a black hole, these tidal effects become extreme. If you were falling feet first toward a black hole, the gravitational pull on your feet would be significantly stronger than the pull on your head, because your feet are closer to the black hole. This differential stretches you vertically while simultaneously compressing you horizontally, a process that has been colorfully named spaghettification. For a stellar mass black hole, these tidal forces would tear apart a human body long before reaching the event horizon. Interestingly, for supermassive black holes, like the one at the center of our galaxy, the event horizon is so large that the tidal forces at the horizon are relatively gentle. You could potentially cross the event horizon of a supermassive black hole without immediately being torn apart by tidal forces. The spaghettification would come later as you continue to fall toward the central singularity. The warping of space-time also affects the very concept of simultaneity. Events that appear to happen at the same time for one observer may not be simultaneous for another observer in a different gravitational field. This breakdown of universal simultaneity means that the question, what is happening right now inside the black hole, has no definitive answer. The answer depends on who is asking and where they are located relative to the black hole. For light, this space-time warping creates effects that challenge our intuitive understanding of how light behaves. We are accustomed to thinking of light as traveling in straight lines at a constant speed. But near a black hole, the straight lines that light follows are actually curved paths through warped space-time. The speed of light, when measured locally, remains constant, but the relationship between space and time becomes so distorted that our usual concepts of speed and distance lose their familiar meanings. One of the most remarkable predictions of general relativity is that light climbing out of a gravitational field loses energy and becomes redshifted. This gravitational redshift is distinct from the Doppler redshift caused by motion. When light escapes from near a black hole, it must climb up the steep gravitational slope of warped space-time, losing energy in the process. The deeper in the gravitational well the light originates, the more energy it loses, and the more redshifted it becomes. As light approaches the event horizon from the outside, this gravitational redshift becomes extreme. Light emitted just outside the event horizon would be so severely redshifted by the time it reaches a distant observer that it would fade away into invisibility. This is one reason why the region just outside a black hole's event horizon appears dark to distant observers, even though it may be filled with matter emitting intense radiation. The frame dragging effect mentioned earlier adds another layer of complexity to the space-time warping around rotating black holes. A rotating black hole literally drags space-time around with it, creating what is known as the lens-Thirring effect. This dragging motion means that nothing can remain stationary relative to distant stars in the region near a rotating black hole. Everything, including light, is forced to orbit in the same direction as the black hole's rotation. This frame dragging creates a region called the ergosphere, located between the event horizon and a boundary called the static limit. Within the ergosphere, the dragging of space-time is so severe that even light must orbit the black hole. This creates the theoretical possibility of extracting energy from a rotating black hole through a process called the Penrose mechanism, where objects dropped into the ergosphere can be ejected with more energy than they had initially. The extreme warping of space-time near a black hole also affects the polarization and propagation of electromagnetic waves. Light waves can become twisted and rotated as they navigate through the curved space-time, effects that astronomers are beginning to detect and use to study the properties of black holes and their surrounding environments. Perhaps most intriguingly, the warping of space-time raises fundamental questions about the nature of information and causality. If space-time can be curved so severely that it forms closed time-like curves, could information from the future influence the past? Could light, following these curved geodesics, arrive at its destination before it departed? These questions touch on some of the deepest puzzles in modern physics and our understanding of the arrow of time. As we consider all these effects of space-time warping, we begin to appreciate just how profoundly different the environment near a black hole is from anything we experience in our everyday lives. The familiar concepts of space, time, and motion become fluid and relative. Light, which normally travels in perfectly straight lines at a constant speed, finds itself navigating a cosmic landscape where straight lines are curved and the very meaning of speed becomes ambiguous. But we have only begun to explore the strange world that exists at the boundary of a black hole. The event horizon itself represents an even more extreme environment. where the warping of space-time reaches its limits and creates phenomena that challenge our deepest understanding of physics. As gravity intensifies near a black hole, it distorts everything, including light. But could this distortion cause light to slow down as it approaches the event horizon? At the edge of every black hole lies an invisible boundary that represents one of the most profound concepts in all of physics, the event horizon. This is not a physical surface that you could touch or see, but rather a mathematical boundary in space-time that defines the ultimate point of no return. Once anything, including light itself, crosses this boundary, it can never escape back to the outside universe. Understanding what happens at this cosmic threshold is crucial to comprehending whether light might behave differently in the extreme environment within a black hole. The term event horizon was coined by physicist Wolfgang Rindler in 1956, but the concept had been understood theoretically for decades before that. The horizon gets its name because it represents the limit of what events can be observed from the outside. Any event that occurs beyond the event horizon can never send information back to the external universe, making it forever hidden from outside observers. To visualize the event horizon, imagine standing at the edge of a waterfall where the water is flowing so fast that anything dropped into it, even something moving upstream as fast as possible, would still be carried over the edge. The event horizon is similar, except instead of water flowing over a cliff, it is space-time itself that is flowing inward toward the black hole's center. At the event horizon, space-time flows inward at exactly the speed of light, making escape impossible for anything, even light itself. The size of the event horizon depends directly on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. This distance, known as the Schwarzschild radius, marks the boundary where the escape velocity equals the speed of light. Double the mass of the black hole, and you double the radius of the event horizon. The supermassive black hole at the center of our galaxy, with its mass of roughly 4 million suns, has an event horizon about the size of Mercury's orbit around our Sun. What makes the event horizon so mysterious is that it appears completely different depending on your perspective. For someone falling into a black hole, crossing the event horizon would seem unremarkable. There would be no wall, no barrier, no sudden change in the local environment. You would simply continue falling inward, completely unaware that you had just crossed the most significant boundary in the universe. The laws of physics would appear to work normally in your immediate vicinity, at least until tidal forces became too strong to survive. However, from the perspective of someone watching from a safe distance, the situation appears entirely different. Due to the extreme gravitational time dilation near the event horizon, an outside observer would see the falling person's motion slow down dramatically as they approached the boundary. The falling person would appear to freeze at the event horizon, their image becoming redder and dimmer over time, but never quite disappearing completely. This difference in perspectives reveals one of the most counterintuitive aspects of black holes. The event horizon is not a universal boundary that everyone agrees upon, but rather a boundary that depends on your reference frame. From outside the black hole, the event horizon represents an impenetrable barrier that nothing can cross in finite time. From inside, it represents a one-way membrane that allows passage inward but never outward. The mathematics describing the event horizon reveals even stranger properties. At the event horizon itself, many of the standard coordinates used to describe space-time become singular, meaning they give infinite or undefined values. This mathematical pathology confused physicists for decades, leading some to wonder whether event horizons could actually exist in nature. It was not until the development of alternative coordinate systems that physicists realized these singularities were merely artifacts of the mathematical description, not physical features of the black hole itself. One of the most remarkable properties of the event horizon is that it has a definite area. and this area can never decrease over time. This is known as Hawking's area theorem, and it has profound implications for our understanding of black holes. When two black holes merge, the area of the resulting event horizon is always greater than the sum of the areas of the original event horizons. When matter falls into a black hole, the event horizon grows to accommodate the additional mass. This behavior of the event horizon area is reminiscent of the behavior of entropy in thermodynamics, where the total entropy of an isolated system can never decrease. This connection led physicists to the startling realization that black holes have temperature and entropy, with the entropy being proportional to the area of the event horizon rather than the volume enclosed by it. This discovery fundamentally changed our understanding of the relationship between gravity, thermodynamics, and information theory. For light specifically, the event horizon represents a profound change in behavior. Light rays that would normally travel in straight lines through empty space become trapped on the event horizon itself. At this boundary, there exist special trajectories called photon spheres, where light can orbit the black hole indefinitely. Any light ray that ventures closer to the black hole than this photon sphere will spiral inward and cross the event horizon, never to escape. The warping of space-time at the event horizon creates what physicists call gravitational redshift to an extreme degree. Light trying to escape from just outside the event horizon must climb out of an increasingly steep gravitational well, losing energy and becoming redshifted in the process. As the light source approaches the event horizon, this redshift becomes infinite, meaning that any light emitted from the horizon itself would be shifted to infinitely long wavelengths and would carry zero energy by the time it reached a distant observer. This infinite redshift is one reason why black holes appear black. It is not that they are made of some dark material, but rather that any light emitted from near the event horizon is redshifted beyond detection. The event horizon represents the boundary where this redshift becomes so extreme that no information can escape to the outside universe. The concept of spaghettification becomes critically important near the event horizon. This colorfully named process describes how tidal forces stretch objects along the direction pointing toward the black hole, while compressing them in the perpendicular directions. For stellar mass black holes, these tidal forces become lethal long before reaching the event horizon. Your feet, being closer to the black hole than your head, would experience significantly stronger gravitational pull, stretching your body beyond its structural limits. However, for supermassive black holes, the situation is dramatically different. The event horizon of a supermassive black hole is so large that the tidal forces at the horizon are relatively gentle. A person could theoretically cross the event horizon of a supermassive black hole and remain intact for some time afterward. The spaghettification would only become fatal much closer to the central singularity. The event horizon also marks the boundary where the concept of time becomes ambiguous. Inside the event horizon, the roles of space and time coordinates become interchanged in a sense. The direction toward the singularity becomes time-like, meaning that falling toward the center becomes as inevitable as moving forward in time. This mathematical role reversal reflects the fact that once inside the event horizon, reaching the singularity is not just probable, but absolutely certain, just as inevitable as aging into the future. For rotating black holes, the structure of the event horizon becomes even more complex. Rotation adds angular momentum to the black hole, which affects the geometry of space-time around it. The event horizon of a rotating black hole is not perfectly spherical, but is instead flattened at the poles and bulged at the equator. The faster the rotation, the more pronounced this distortion becomes. Rotating black holes also possess an additional boundary called the ergosphere, which lies outside the event horizon. Within the ergosphere, the frame dragging effect is so strong that nothing can remain stationary relative to distant stars. Everything within this region must rotate with the black hole, carried along by the twisted space-time. Remarkably, objects can still escape from the ergosphere, unlike the event horizon from which no escape is possible. The quantum nature of the event horizon adds yet another layer of mystery. According to quantum field theory, particle pairs are constantly being created and annihilated throughout empty space due to quantum fluctuations. Near the event horizon, these quantum effects create what is known as Hawking radiation. One particle from a quantum pair can fall into the black hole while the other escapes, causing the black hole to slowly evaporate over incredibly long periods of time. This Hawking radiation means that the event horizon is not completely black after all. It emits a faint thermal radiation with a temperature inversely proportional to the black hole's mass. For stellar mass black holes, this temperature is incredibly tiny, much colder than the cosmic microwave background radiation that fills the universe. But for microscopic black holes, if they exist, the temperature could be enormous, causing them to evaporate explosively. The information paradox represents one of the most profound puzzles associated with event horizons. If information that falls into a black hole is destroyed when the black hole evaporates through Hawking radiation, this would violate one of the fundamental principles of quantum mechanics, the conservation of information. This paradox has sparked decades of debate among physicists and has led to new ideas about the nature of space-time, quantum mechanics, and the holographic principle. Some theories suggest that information is not actually destroyed, but is somehow encoded on the event horizon itself, much like a hologram stores three-dimensional information on a two-dimensional surface. This holographic principle has far-reaching implications, suggesting that all the information contained within any region of space can be encoded on its boundary. If true, this would fundamentally change our understanding of how information and reality are structured. The event horizon also plays a crucial role in the firewall paradox, a recent puzzle in black hole physics. If Hawking radiation is entangled with the interior of the black hole, and if information must be preserved, then quantum mechanics seems to predict that the event horizon should be filled with high-energy particles that would incinerate anything trying to cross it. This conflicts with the equivalence principle, which states that falling through the event horizon should feel no different from free fall in empty space. As we contemplate the mysterious nature of the event horizon, we begin to understand why it represents such a profound boundary in our universe. It is not just a point of no return for matter and energy, but a boundary where our fundamental concepts of space, time, causality, and information are challenged and transformed. The event horizon marks the edge of the knowable universe, beyond which the normal rules of physics may no longer apply. For light, the event horizon represents the ultimate test. Having traveled freely through the universe at its constant speed for billions of years, light suddenly encounters a boundary where escape becomes impossible. But what happens to light once it crosses this threshold? Does it maintain its fundamental properties? Or does the extreme environment inside a black hole alter the very nature of light itself? Once past the event horizon, the laws of physics break down. But could light, which is normally bound by the speed of space-time, be affected by the extreme warping inside? Now we arrive at the heart of our cosmic mystery. For billions of years, light has traveled through the universe at its unwavering speed of 299,792,458 meters per second. This speed has been the one true constant, the universal speed limit that governs all of reality. But what happens when light encounters the most extreme gravitational environment in the universe? Could the intense curvature of space-time inside a black hole actually cause light to slow down, or even stop entirely? To explore this question, we must first understand what we mean when we talk about the speed of light. In everyday language, speed seems straightforward. It is simply distance divided by time. But near a black hole, both distance and time become fluid concepts that depend entirely on your perspective and location. The very fabric of space-time becomes so warped that our usual notions of measurement break down completely. From the perspective of someone falling into a black hole, equipped with local measuring instruments, light would still appear to travel at its normal speed. If you shined a flashlight while falling past the event horizon, the light would move away from you at exactly the speed of light, just as it would anywhere else in the universe. This is a consequence of the equivalence principle, one of the fundamental insights of general relativity. Locally, in any small region of space-time, the laws of physics appear normal, regardless of how curved space-time might be on larger scales. However, the situation becomes far more complex when we consider what a distant observer would measure. Due to the extreme gravitational time dilation near a black hole, clocks run slower in stronger gravitational fields. From the perspective of someone safely outside the black hole, time itself appears to slow down near the event horizon. If time is running slower and light is traveling a certain distance in that slower time, then light appears to be moving more slowly when measured by the distant observer's clocks and rulers. This creates a fascinating paradox. Light always travels at the speed of light locally, but can appear to travel slower when measured from a different reference frame. This apparent contradiction reveals the deep truth that speed, like time itself, is not absolute, but depends entirely on your frame of reference. Near a black hole, the extreme curvature of space-time makes this relativity of measurement dramatically apparent. Consider a photon of light emitted from just outside the event horizon of a black hole. As this photon climbs out of the intense gravitational field, it must work against the curvature of space-time itself. In doing so, it loses energy, becoming redshifted to longer and longer wavelengths. From the perspective of a distant observer, this redshifted light appears to be moving more slowly as it struggles against the gravitational field. But here is where the physics becomes truly mysterious. As light approaches the event horizon from the outside, the gravitational redshift becomes more and more extreme. The light becomes redder and redder, losing energy continuously as it tries to escape the black hole's gravitational grip. To a distant observer, the light appears to slow down dramatically, taking longer and longer to travel each additional unit of distance as it approaches the horizon. At the event horizon itself, this effect becomes infinite. Light emitted exactly at the event horizon would be infinitely redshifted, meaning it would have zero energy and would appear to a distant observer to be completely motionless. This suggests that from the outside perspective, light effectively stops at the event horizon, never quite crossing the boundary in any finite amount of time. Yet this is only part of the story. The situation inside the event horizon is even more extraordinary. Once light crosses this boundary, it finds itself in a region of space-time where the normal rules of escape no longer apply. The curvature of space-time is so extreme that all paths, even those followed by light, lead inexorably toward the central singularity. In this sense, light inside a black hole is not just slowed down, it is trapped on a one-way journey toward infinite density. The warping of space-time inside a black hole affects light in ways that challenge our fundamental understanding of how electromagnetic radiation behaves. The paths that light follows, called geodesics, become increasingly curved as the light spirals inward toward the singularity. These geodesics represent the straightest possible paths through curved space-time. But in the extreme environment inside a black hole, even the straightest path becomes a spiral toward the center. As light travels along these curved geodesics, the very meaning of speed becomes ambiguous. In normal space-time, we can define speed as the rate at which light covers distance over time. But inside a black hole, space and time themselves become so distorted that the usual coordinate systems break down. The radial coordinate, which normally measures distance from the center, becomes time-like inside the event horizon, meaning that moving toward the center becomes as inevitable as moving forward in time. This coordinate mixing has profound implications for how we understand light's behavior inside a black hole. The direction toward the singularity becomes a time direction rather than a space direction. Light is not just moving through space toward the center. It is being carried forward in time toward an inevitable encounter with infinite curvature. In this strange environment, the question of whether light slows down becomes as complex as asking whether time itself can slow down. Some theoretical physicists have proposed that the extreme conditions inside a black hole might actually alter the fundamental properties of light itself. In the region near the singularity, where space-time curvature approaches infinity, the normal laws of physics may break down completely. Quantum effects, normally negligible on macroscopic scales, might become dominant in this extreme environment, potentially affecting how light propagates through space. The uncertainty principle of quantum mechanics suggests that, at incredibly small scales of space and time, the very concepts of precise position and momentum become meaningless. Near the singularity of a black hole, space-time itself might become subject to quantum fluctuations, creating a foam-like structure where the smooth geometry assumed by general relativity no longer applies. In such an environment, light might not travel along well-defined paths, but could instead be subject to quantum uncertainties that affect its speed and direction. Another possibility is that the intense gravitational fields inside a black hole might create conditions where the effective speed of light in the medium becomes different from its value in empty space. While light in vacuum always travels at the same speed locally, light traveling through matter or through regions of intense electromagnetic fields can have an effective speed that differs from the vacuum value. Some theories suggest that the extreme curvature of space-time itself might act like a medium that affects light propagation. The phenomenon of gravitational lensing provides another perspective on how black holes affect light. As light passes through the curved space-time around a black hole, its path is bent and focused, similar to how light is bent by a glass lens. But unlike a glass lens, which slows light down by allowing it to interact with the atoms in the glass, gravitational lensing bends light without changing its local speed. The light follows curved geodesics through space-time while maintaining its characteristic velocity along those paths. However, the global properties of light propagation can still be affected. Light that takes a longer, more curved path around a black hole will take more time to reach its destination than light that travels along a shorter, straighter path. From the perspective of measuring travel time over large distances, this could be interpreted as an effective slowing of light, even though the local speed remains constant. The extreme tidal forces near a black hole add another layer of complexity to understanding light's behavior. These forces, which stretch space in one direction while compressing it in perpendicular directions, can affect the polarization and propagation of electromagnetic waves. Light waves themselves can be stretched and compressed by these tidal effects, potentially altering their wavelength and frequency in ways that affect how we measure their speed. Some of the most exotic proposals suggest that black holes might create regions where the effective dimensionality of space-time is altered. In our normal experience, light travels through three-dimensional space over one-dimensional time. But in the extreme environment near a singularity, the structure of space-time itself might be fundamentally different, with additional dimensions becoming relevant, or existing dimensions becoming compactified. In such scenarios, light might be forced to travel through a higher dimensional space, effectively slowing its progress through our familiar three-dimensional world. The holographic principle which suggests that all information in a volume of space can be encoded on its boundary, raises intriguing questions about light's behavior inside black holes. If the event horizon acts as a holographic screen that contains all the information about the black hole's interior, then light inside the black hole might not have independent existence, but could instead be a projection from information stored on the horizon. This would fundamentally alter our understanding of what it means for light to have a speed inside a black hole. Recent advances in black hole thermodynamics have revealed that black holes have temperature and entropy, suggesting that they are not empty voids, but rather complex thermodynamic systems. The thermal radiation predicted by Stephen Hawking emerges from quantum effects near the event horizon and has a well-defined temperature. This thermal environment might affect how light propagates, similar to how light travels differently through hot gases compared to cold vacuum. The information paradox associated with black holes also bears on the question of light's speed. If information cannot be destroyed, then light falling into a black hole must somehow preserve the information it carries. Some proposed solutions to this paradox involve mechanisms that would fundamentally alter how light behaves inside black holes, potentially affecting its speed or even its ability to maintain coherent propagation toward the singularity. As we consider all these possibilities, we begin to appreciate just how profound and complex the question of light's speed inside a black hole truly is. The answer depends not just on our understanding of gravity and space-time, but on the fundamental nature of quantum mechanics, thermodynamics, and information theory. The extreme environment inside a black hole represents a testing ground for our most advanced theories of physics, where the normal rules may no longer apply. What emerges from this investigation is not a simple answer, but rather a deeper appreciation for the mysteries that black holes represent. They are not just exotic objects in distant space, but laboratories where the fundamental laws of nature are pushed to their absolute limits. The question of whether light slows down inside a black hole touches on some of the deepest puzzles in modern physics, and may ultimately require new theories that unify gravity with quantum mechanics to fully resolve. Could light, so constant in our universe, experience changes in its speed within a black hole? If so, what would that mean for our understanding of space and time? At the very heart of every black hole lies perhaps the most mysterious and challenging concept in all of physics: the singularity. This is a region where the normal laws of physics break down completely, where matter is compressed to infinite density, and where space-time curvature becomes infinite. It is here, in this realm beyond the reach of our current understanding, that we must confront the ultimate question of what happens to light when it encounters the most extreme conditions imaginable in our universe. A singularity represents the mathematical breakdown of our theories. When physicists solve Einstein's equations for the interior of a black hole, they find that at the center, the curvature of space-time becomes infinite. All the matter that has ever fallen into the black hole is predicted to be crushed down to a point of zero volume and infinite density. This is not just extremely dense, like the core of a neutron star, but literally infinite density, a concept that challenges our very understanding of what matter and space can be. The journey to the singularity begins the moment anything crosses the event horizon. Unlike the event horizon itself, which represents a boundary rather than a physical place, the singularity appears to be an actual destination, an endpoint that everything inside the black hole must eventually reach. The warped geometry of space-time inside the event horizon ensures that all paths, regardless of their initial direction, eventually converge at this central point of infinite curvature. For light, this presents a profound mystery. Throughout its existence, light has followed geodesics, the straightest possible paths through space-time. But what happens when these geodesics lead to a point where space-time itself becomes infinitely curved? Can light continue to exist in an environment where the very fabric of reality breaks down? does the singularity represent the ultimate end of light's journey, a cosmic terminus where photons cease to exist? The mathematics describing the approach to a singularity reveals a countdown to infinity that defies physical intuition. As matter or energy falls toward the center of a black hole, the tidal forces become stronger and stronger. Any extended object, whether a star, a planet, or even a beam of light with finite width, experiences increasingly extreme stretching along the direction of fall and compression in the perpendicular directions. These forces grow without limit as the singularity approaches. But the nature of the singularity itself remains deeply mysterious. The infinite density predicted by general relativity is almost certainly not physically realistic. Most physicists believe that before true infinite density is reached, quantum effects must become important and modify the classical description. The problem is that we do not yet have a complete theory of quantum gravity that can tell us what actually happens in this extreme regime. One possibility is that the singularity is not a point, but rather a region, where space-time has a fundamentally different structure than we are familiar with. Some theories suggest that at the scales where quantum gravity becomes important, space and time themselves might be discrete rather than continuous, made up of tiny indivisible units rather than forming a smooth fabric. In such a picture, the singularity might represent a breakdown of our continuous description of space-time, rather than a true physical infinity. Another intriguing possibility is that singularities might be naturally avoided by quantum effects. The uncertainty principle of quantum mechanics prevents us from precisely determining both the position and momentum of any particle. As matter is compressed toward the singularity, quantum uncertainties might become so large that the very concept of a definite location breaks down. This could prevent the formation of true singularities and replace them with regions of finite but extremely high density. For light approaching a singularity, quantum effects might become crucial in unexpected ways. Light consists of photons, which are quantum particles of electromagnetic radiation. Near the singularity, the extreme curvature of space-time might cause photons to interact with the quantum vacuum in novel ways. Virtual particle pairs, constantly being created and destroyed throughout empty space, might be affected by the intense gravitational field, potentially altering how light propagates through this region. The concept of time becomes particularly strange near a singularity. From the perspective of an outside observer, anything falling into a black hole appears to slow down and freeze at the event horizon due to gravitational time dilation. But from the perspective of someone falling in, the journey to the singularity takes only a finite amount of proper time. For a stellar mass black hole, this journey from event horizon to singularity might take only milliseconds, while for a supermassive black hole, it could take hours. This raises fascinating questions about light's experience near the singularity. If light has any kind of perspective, what would it experience during this final journey? Would it encounter the singularity in a finite time, or would quantum effects or other unknown physics intervene before that point? The fact that photons themselves experience no passage of time in their own reference frame adds another layer of mystery to this question. The singularity also represents a boundary for information and causality. Once information falls into a black hole and approaches the singularity, it becomes completely cut off from the outside universe. No signal can escape from inside the event horizon to tell us what happens near the singularity. This creates a fundamental limit on what we can know about these regions, even in principle. The singularity exists beyond the edge of the observable universe, in a realm that is forever hidden from direct investigation. Some theories propose that singularities might be connected to other regions of space-time through structures called wormholes. These hypothetical tunnels through space-time could potentially allow matter and energy, including light, to travel from one black hole to another distant region of the universe, or even to another universe entirely. While no evidence exists for such connections, they remain intriguing theoretical possibilities that could dramatically alter our understanding of what happens to light inside black holes. The holographic principle suggests another perspective on singularities and the fate of light within black holes. According to this principle, all the information contained within a black hole can be encoded on its two-dimensional event horizon, much like a hologram encodes three-dimensional information on a flat surface. This would imply that light falling toward the singularity does not actually carry independent information, but rather contributes to the information content stored on the horizon surface. If the holographic principle is correct, then the question of what happens to light at the singularity might be misguided. The light might not actually reach a physical singularity, but instead might be part of a holographic projection from information stored on the event horizon. This would fundamentally change our understanding of the black hole interior and suggest that the singularity might not be a real physical entity, but rather an artifact of our incomplete understanding. The firewall paradox, a recent puzzle in black hole physics, also bears on the fate of light near singularities. This paradox arises from trying to reconcile the requirements of quantum mechanics with the smooth passage through the event horizon predicted by general relativity. Some proposed solutions involve the creation of a firewall of high-energy particles at the event horizon that would destroy any information, including light, before it could reach the singularity. The thermodynamic properties of black holes add yet another dimension to understanding singularities. Black holes have temperature and entropy, and they evaporate through Hawking radiation over extremely long timescales. This means that black holes are not permanent features of the universe, but rather slowly shrinking objects that will eventually disappear completely. What happens to the information contained in the singularity when the black hole finally evaporates remains one of the deepest puzzles in theoretical physics. For very small black holes, if they exist, the evaporation process could be rapid and explosive. As a black hole loses mass through Hawking radiation, its temperature increases, causing it to radiate even faster in a runaway process. In the final moments of such evaporation, the extreme energies involved might create conditions where our understanding of physics breaks down even more dramatically than at the singularity itself. The study of singularities has led to important mathematical insights about the general behavior of space-time under extreme conditions. The singularity theorems, proven by Stephen Hawking and Roger Penrose in the 1960s, demonstrate that singularities are inevitable consequences of general relativity under very general conditions. These theorems show that singularities are not just mathematical curiosities, but fundamental features of Einstein's theory of gravity. However, these same theorems also highlight the limits of general relativity. The presence of singularities in the theory indicates places where the theory predicts its own breakdown. This is similar to how classical physics breaks down at the atomic scale, requiring quantum mechanics for a complete description. The existence of singularities suggests that general relativity must eventually be replaced by a more fundamental theory, probably involving quantum gravity, for a complete understanding of these extreme regions. Various approaches to quantum gravity offer different perspectives on what might replace the classical singularity. String theory, loop quantum gravity, and other approaches each make different predictions about the nature of the black hole interior. Some suggest that singularities are replaced by regions of finite curvature. Others propose that space and time themselves have discrete structures at the smallest scales. And still others suggest that the interior might be connected to other regions of space-time in unexpected ways. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that nature somehow conspires to hide singularities behind event horizons, preventing them from being directly observable from the outside universe. This hypothesis, while not proven, seems to hold in all known cases and suggests that singularities might represent a fundamental boundary of the knowable universe, forever hidden from direct observation and study. As we contemplate the mystery of singularities, we are forced to confront the limits of human knowledge and understanding. These regions represent the ultimate frontier of physics, where our most successful theories break down and point toward new physics that we have yet to discover. They are cosmic laboratories where the fundamental nature of space, time, matter, and energy are tested under the most extreme conditions imaginable. For light, the singularity represents the ultimate unknown. After traveling freely through the universe for billions of years, after maintaining its constant speed through every environment it has encountered, light finally faces a region where the very concepts of speed, distance, and time lose their familiar meanings. Whether light is destroyed, transformed, or transported elsewhere when it encounters a singularity remains one of the deepest mysteries in physics. At the singularity, the laws of physics no longer apply as we know them. Could light, when trapped by the singularity's gravity, simply cease to exist or lose its speed altogether? Light, at its most fundamental level, consists of particles called photons. These are not little balls of light traveling through space, but rather quantum objects that embody the strange duality between particle and wave that characterizes all quantum phenomena. A single photon can be in multiple states simultaneously, can tunnel through barriers that should be impenetrable, and can become entangled with other photons across vast distances in ways that Einstein famously called spooky action at a distance. This quantum nature of light becomes particularly intriguing when we consider what happens inside a black hole. In normal circumstances, the quantum properties of light are often overshadowed by its classical behavior. Light waves propagate predictably through space, follow well-defined paths, and carry energy and information in ways that can be calculated using the equations of classical electromagnetism. But inside a black hole, where space-time itself becomes quantum mechanical near the singularity, the quantum nature of light might become dominant. The uncertainty principle, one of the fundamental tenets of quantum mechanics, states that certain pairs of properties cannot be measured simultaneously with perfect precision. For photons, this means that we cannot know both their exact position and their exact momentum at the same time. The more precisely we try to determine where a photon is, the less precisely we can know where it is going and how fast. This uncertainty is not due to limitations in our measuring instruments, but is a fundamental feature of reality itself. Near the singularity of a black hole, this quantum uncertainty might have profound implications. As space-time curvature becomes extreme, the very concepts of position and momentum that we use to describe photon behavior might break down. The uncertainty principle could prevent photons from being localized precisely enough to reach a true mathematical singularity. Instead, quantum effects might spread the photon's probability over a finite region, preventing the infinite densities that classical physics predicts. The process of quantum tunneling adds another layer of mystery to light's behavior inside black holes. In quantum mechanics, particles can sometimes pass through barriers that classical physics says should be impenetrable. This happens because the wave function that describes a quantum particle can extend beyond classical boundaries, allowing for a small but non-zero probability that the particle will appear on the other side of a barrier. Could quantum tunneling allow light to escape from inside a black hole? At first glance, this seems impossible, since the event horizon represents an absolute boundary from which nothing can escape. But some theories suggest that quantum effects near the event horizon might create opportunities for information, if not actual photons, to tunnel out of the black hole. This quantum tunneling might be related to the Hawking radiation that black holes emit, where quantum fluctuations near the event horizon create particle pairs, one of which escapes while the other falls in. The The concept of virtual particles becomes crucial when considering quantum effects inside black holes. Throughout empty space, particle-antiparticle pairs are constantly being created and annihilated on timescales so short that they cannot be directly observed. These virtual particles contribute to the quantum vacuum energy and can become real under extreme conditions. Near the event horizon of a black hole, the intense gravitational field can promote virtual photons to real photons, creating the Hawking radiation that causes black holes to slowly evaporate. Inside the black hole, these virtual particle effects might be even more dramatic. The extreme curvature of space-time could create conditions where virtual photons interact with the gravitational field in ways that alter their properties. The boundary between virtual and real particles might become blurred in the quantum foam that some theories predict exists near the singularity. In this environment, the very concept of what constitutes a photon might need to be redefined. Quantum field theory, which describes how quantum particles behave in curved spacetime, predicts that the vacuum itself can become excited by strong gravitational fields. This means that even empty space inside a black hole might be filled with quantum fluctuations of electromagnetic fields. These fluctuations could interact with any light falling into the black hole, potentially altering its propagation in ways that classical physics cannot predict. The phenomenon of quantum decoherence also plays a role in understanding light's behavior inside black holes. Decoherence occurs when a quantum system becomes entangled with its environment, causing the system to lose its quantum coherence and behave more classically. Inside a black hole, light would be constantly interacting with the curved spacetime and any matter present, potentially causing rapid decoherence that might alter how we understand its quantum properties. Quantum entanglement represents one of the most mysterious aspects of quantum mechanics and might be crucial for understanding what happens to light inside black holes. When two photons become entangled, their properties become correlated in ways that persist even when they are separated by vast distances. If one photon from an entangled pair falls into a black hole while the other remains outside, what happens to their entanglement? This question is central to the information paradox and might hold clues about whether information can truly be destroyed inside black holes. Some theories propose that the interior of a black hole might be connected to its exterior through quantum entanglement rather than through classical spacetime geometry. In this view, light falling into a black hole might not actually travel to a physical singularity, but instead might become entangled with the degrees of freedom on the event horizon. This would fundamentally change our understanding of what it means for light to have a speed or location inside a black hole. The holographic principle, which suggests that the information in any volume of space can be encoded on its boundary, takes on special significance when considering the quantum nature of light inside black holes. If this principle is correct, then light inside a black hole might not have independent existence, but might instead be a holographic projection from quantum information stored on the event horizon. In this picture, asking about the speed of light inside a black hole might be like asking about the speed of images projected by a hologram. Quantum gravity theories offer various perspectives on how light might behave in the extreme environment near a black hole singularity. String theory, which proposes that fundamental particles are actually tiny vibrating strings, suggests that at the smallest scales, space-time itself might have a stringy structure. In this framework, photons would be particular vibration modes of these strings, and their behavior in extremely curved space-time might be fundamentally different from what classical or even ordinary quantum field theory predicts. Loop quantum gravity takes a different approach, suggesting that space and time are quantized at the smallest scales, made up of discrete units rather than forming a continuous fabric. In this theory, the singularity at the center of a black hole would be replaced by a quantum bounce, where matter reaching maximum density would rebound and potentially emerge from a white hole in another region of space-time. Light falling into such a black hole might not be destroyed, but could be transported to another universe or another region of our own universe. The concept of black hole complementarity proposes that the same physics can be described from multiple perspectives that seem contradictory, but are actually equivalent. From the perspective of an outside observer, information falling into a black hole is encoded on the event horizon and eventually escapes through Hawking radiation. From the perspective of someone falling in, the information passes smoothly through the event horizon and hits the singularity. Light might exist in both descriptions simultaneously, appearing to slow down and stop at the horizon from one perspective while continuing to travel at normal speed from another. Quantum error correction, borrowed from quantum computing theory, has recently been applied to understand how information might be preserved inside black holes. Just as quantum computers use error correction codes to protect information from decoherence, black holes might use similar quantum codes to preserve information that falls into them. Light carrying information into a black hole might be encoded in ways that allow the information to be recovered even after the black hole evaporates, though the original photons themselves might be fundamentally transformed in the process. The firewall paradox highlights the tension between different quantum mechanical requirements for black holes. If information must be preserved, and Hawking radiation must be thermal, then quantum mechanics seems to require that the event horizon be filled with high-energy photons that would destroy anything trying to cross it. This paradox suggests that our understanding of how light behaves near event horizons might be fundamentally incomplete and might require new insights about the quantum nature of spacetime itself. Recent developments in quantum information theory have suggested that the interior of a black hole might emerge from quantum entanglement between different regions of the event horizon. In this view, space itself is woven from quantum entanglement, and the smooth spacetime that light travels through is an emergent property of more fundamental quantum correlations. Inside a black hole, where these entanglement patterns might be disrupted, the very notion of space through which light travels might break down. The study of analog black holes, created in laboratory settings using fluids or ultra-cold gases, has provided new insights into how quantum effects might manifest in black hole-like environments. These systems can simulate some aspects of the event horizon and allow researchers to study how waves, analogous to light, behave when they cannot escape from a region. While these analog systems cannot fully capture the complexity of real black holes, they suggest that quantum effects can indeed alter wave propagation in dramatic ways. As we explore these quantum mechanical perspectives on light inside black holes, we begin to see that the question of whether light slows down might be too simplistic. The quantum nature of light suggests that inside a black hole, photons might exist in superposition states, might tunnel through space-time barriers, might become entangled with the black hole's degrees of freedom, or might even cease to exist as independent entities and become part of a larger quantum system. The extreme environment inside a black hole represents a testing ground for our most advanced theories of quantum mechanics and gravity. It is a place where the classical concepts of particles traveling through space might give way to more exotic quantum phenomena that we are only beginning to understand. The fate of light inside black holes might ultimately teach us not just about gravity and space-time, but about the fundamental quantum nature of reality itself. Could quantum mechanics hold the answer to understanding light's behavior inside a black hole? The intersection of quantum physics and gravity could reveal secrets we have yet to imagine. The greatest irony in studying black holes lies in the fundamental challenge of observing objects that, by their very nature, do not emit light. How do you see something that is invisible? How do you study the behavior of light inside a region from which no light can escape? These questions have driven astronomers to develop ingenious methods for detecting and studying black holes, methods that rely on the very light that these cosmic giants seem to devour so completely. For decades, black holes existed only in the realm of theoretical physics, mathematical solutions to Einstein's equations that seemed too strange to exist in the real universe. The idea that there could be objects so massive and compact that not even light could escape seemed almost like science fiction. Yet astronomers persisted in their search, knowing that if black holes truly existed, they would leave unmistakable signatures in the cosmos, fingerprints of their presence, written in the language of light itself. The key insight that made black hole astronomy possible was the realization that while we cannot see black holes directly, we can observe their effects on their surroundings. Black holes may be invisible, but they are not inactive. Their immense gravitational fields affect everything around them, bending the paths of light, accelerating matter to incredible speeds, and heating gas to temperatures of millions of degrees. It is through these effects that black holes reveal themselves to our telescopes. One of the most dramatic ways black holes announce their presence is through their interactions with nearby stars. When a black hole and a normal star orbit each other in a binary system, the black hole's gravity can strip material from its stellar companion. This stolen matter does not fall directly into the black hole, but instead forms a swirling disk called an accretion disk. As matter in this disk spirals inward toward the event horizon, it accelerates to tremendous speeds and heats up due to friction and compression. The temperatures in these accretion disks can reach tens of millions of degrees, hot enough to emit intense X-rays and ultraviolet radiation. This is light of the most energetic kind, photons carrying far more energy than the visible light our eyes can detect. Ironically, regions very close to black holes, where light itself cannot escape, become some of the brightest objects in the universe when viewed from a distance. The light comes not from inside the black hole, but from the matter racing around its edge. Matter that has been heated to incandescence by the black hole's immense gravity. The study of this radiation has revealed intimate details about the environment just outside black holes. Astronomers can measure the Doppler shifts in the light from accretion disks to determine how fast matter is moving as it orbits the black hole. They can observe how the light is red-shifted by the black hole's gravity and how it is bent and focused by gravitational lensing effects. These observations provide indirect but powerful evidence for the existence of event horizons and the extreme warping of space-time that black holes create. The first convincing black hole candidate was discovered in 1971, an X-ray source called Cygnus X1. Astronomers observed a visible star that appeared to be orbiting an invisible companion, and the orbital dynamics indicated that this invisible object had far too much mass to be a neutron star or any other known type of stellar remnant. The only explanation that fit the observations was that the invisible companion was a black hole, stripping matter from its stellar partner and heating it to X-ray emitting temperatures. Since then, astronomers have discovered thousands of black hole candidates using similar techniques. They look for X-ray sources that show the characteristic signatures of matter falling into extremely compact objects. They search for stars with unusual orbital motions that suggest they are dancing with invisible partners. They study the spectra of light from these systems, looking for the telltale signs of extreme gravitational redshift and Doppler shifting that indicate the presence of event horizons. One of the most remarkable discoveries in black hole astronomy came from studying the center of our own galaxy. For decades, astronomers tracked the motions of stars near the galactic center, watching them follow elliptical orbits around an invisible object. By carefully measuring the speeds and orbital periods of these stars, they were able to calculate the mass of the central object. The result was stunning. 4 million times the mass of our Sun, concentrated in a region smaller than our solar system. No known object except a black hole could be so massive and so compact. The study of these galactic center stars provided some of the most direct evidence for the existence of black holes and offered unique insights into how light behaves in strong gravitational fields. As these stars swung close to the black hole in their elliptical orbits, astronomers could observe how their light was affected by the extreme gravity. They saw gravitational redshift as starlight climbed out of the black hole's gravitational well, and they observed relativistic effects as the stars reached speeds approaching a significant fraction of the speed of light. Radio astronomy has provided another powerful tool for studying black holes. Many black holes, particularly the supermassive ones at the centers of galaxies, launch powerful jets of material at speeds close to the speed of light. These jets emit intense radio waves and can extend for millions of light years from the black hole that created them. By studying these radio emissions, astronomers can probe the immediate environment around black holes and understand how they interact with their host galaxies. The development of interferometry, a technique that combines signals from multiple telescopes to create images with unprecedented resolution, revolutionized black hole astronomy. By linking radio telescopes around the world, astronomers created the Event Horizon Telescope, an Earth-sized virtual telescope capable of resolving features as small as the event horizons of the nearest supermassive black holes. This technical achievement led to one of the most significant breakthroughs in astronomy, the first direct images of black hole event horizons. In 2019, the Event Horizon Telescope captured the first image of the supermassive black hole at the center of the galaxy, Messier 87. The image showed a dark shadow surrounded by a bright ring of glowing gas, exactly as predicted by decades of theoretical work. This was not just a photograph, but a direct confirmation that event horizons exist and that black holes have the properties that Einstein's theory predicted over a century ago. The shadow in these images represents the photon sphere, the region around a black hole where light can orbit indefinitely. Light from beyond this sphere can escape to reach our telescopes, but light from within it is doomed to spiral into the black hole. The boundary between light and dark in these images marks the edge of the observable universe around a black hole, the point beyond which no information can ever reach us. These direct images revealed subtle but important details about how light behaves near black holes. The asymmetry in the brightness of the ring around the black hole shadow showed the effects of relativistic beaming, where light from matter moving toward us appears brighter than light from matter moving away. The polarization of this light provided information about the magnetic fields threading through the accretion disk, fields that play a crucial role in channeling matter toward the black hole and launching the powerful jets that extend far into intergalactic space. Gravitational wave astronomy has opened yet another window into the world of black holes. When two black holes spiral into each other and merge, they create ripples in space-time itself that can be detected by incredibly sensitive instruments like LIGO and Virgo. These gravitational waves carry information about the masses, spins, and orbital dynamics of merging black holes, providing insights that are impossible to obtain through electromagnetic observations alone. The detection of gravitational waves from black hole mergers has confirmed many predictions of general relativity and has revealed a previously unknown population of black holes with masses between those of stellar remnants and supermassive galactic black holes. These observations have also provided new tests of how space-time behaves under the most extreme conditions, validating our understanding of the gravitational effects that govern light's behavior near black holes. Multi-messenger astronomy, which combines observations of gravitational waves, electromagnetic radiation, and other signals, is beginning to provide a comprehensive picture of black hole environments. By observing the same events through multiple channels, astronomers can study how matter, energy, and information flow in the vicinity of black holes, and can test our theories of how these extreme objects interact with their surroundings. The challenges of observing black holes have driven remarkable innovations in telescope technology. Adaptive optic systems correct for the blurring effects of Earth's atmosphere, allowing ground-based telescopes to achieve theoretical resolution limits. Space-based telescopes avoid atmospheric interference entirely and can observe wavelengths of light that are absorbed by the atmosphere. Future missions will push these capabilities even further, potentially allowing us to study the immediate vicinity of black holes in unprecedented detail. One of the most intriguing prospects for future black hole observations is the possibility of detecting individual photons that have been gravitationally lensed by black holes. As light from distant sources passes near black holes, it can be bent and focused in ways that create multiple images or dramatically magnify the apparent brightness of background objects. By studying these lensing effects in detail, astronomers hope to probe the structure of space-time around black holes with exquisite precision. The study of black hole accretion disks has revealed that these systems are incredibly dynamic, with brightness variations on timescales ranging from milliseconds to years. These variations provide information about the structure and dynamics of matter very close to event horizons, regions where the effects of general relativity are most pronounced. By correlating these variations across different wavelengths of light, astronomers can map the flow of matter in the final moments before it disappears behind the event horizon. Perhaps most remarkably, astronomers are now able to study how the properties of space and time themselves are affected by black holes. By precisely measuring the orbits of stars and gas clouds around black holes, they can test Einstein's predictions about frame dragging, gravitational time dilation, and the bending of space-time. These observations provide direct empirical tests of general relativity in the strong field regime, where deviations from Einstein's theory would have the most dramatic consequences. The infrared and X-ray monitoring of matter falling into black holes has revealed phenomena that challenge our understanding of how these systems work. Matter does not fall smoothly into black holes, but instead shows complex patterns of variability that suggest the presence of magnetic fields, turbulence, and possibly relativistic effects that alter the flow of material near the event horizon. These observations hint at rich physics occurring in the region where light makes its final journey toward the point of no return. As our observational capabilities continue to improve, we are approaching the point where we might be able to test some of the more exotic predictions about black hole physics. Future telescopes might be sensitive enough to detect the subtle effects of Hawking radiation from nearby black holes, or to observe the predicted precession of orbits around rotating black holes. These observations could provide crucial tests of our understanding of how quantum mechanics and general relativity interact in extreme environments. The quest to observe black holes has taught us that while we cannot see inside these cosmic giants, the light that surrounds them tells a rich and complex story. Every photon that escapes from near a black hole carries information about the extreme conditions it encountered. Information that we are learning to decode with increasing sophistication. Through this light, we can probe the very limits of space and time and test our understanding of the fundamental laws that govern the universe. Though we cannot see inside a black hole, light's behavior around it tells us volumes about what is happening beyond the event horizon. But what happens to light once it crosses this boundary? As we venture deeper into the theoretical landscape surrounding black holes, we encounter one of the most profound questions in modern physics. What exactly happens to light once it crosses the event horizon and becomes trapped within a black hole? This question touches on fundamental issues of information, energy conservation, and the ultimate fate of matter and radiation in the universe. The various theoretical possibilities that physicists have proposed reveal just how strange and counterintuitive the interior of a black hole might truly be. The classical view of general relativity presents a seemingly straightforward answer. Once light crosses the event horizon, it becomes trapped on inexorable geodesics that lead toward the central singularity. In this picture, photons continue to travel at the speed of light along their curved space-time paths. But these paths all converge toward a point of infinite density and curvature. The light would be compressed and concentrated, along with all other matter and energy that has ever fallen into the black hole, ultimately reaching a state that defies physical understanding. But this classical picture raises immediate questions about what happens to the information carried by light. Every photon encodes information about its source, its energy, its polarization, and its history. If this information is simply crushed out of existence at the singularity, it would violate one of the most fundamental principles of quantum mechanics, the conservation of information. This tension between general relativity and quantum mechanics has driven decades of theoretical research into alternative possibilities for light's fate inside black holes. One intriguing possibility is that light becomes trapped not at a point singularity, but within a more complex structure that preserves information while preventing escape. Some theories suggest that the extreme curvature near the center of a black hole might create closed time-like curves, regions where space-time becomes so twisted that past and future become intertwined. In such a scenario, light might become trapped in temporal loops, circling endlessly through time rather than space, never quite reaching a final destination. The concept of quantum entanglement offers another perspective on how light might be trapped inside black holes. When light becomes entangled with other quantum systems, its information becomes distributed across multiple particles or fields. Some theoretical models suggest that light falling into a black hole becomes maximally entangled with the quantum degrees of freedom that exist on the event horizon. In this picture, the light is not destroyed, but rather becomes part of a vast quantum network that encompasses the entire black hole system. The holographic principle presents perhaps the most radical reimagining of what it means for light to be trapped in a black hole. According to this principle, all the information contained within the three-dimensional volume of a black hole can be encoded on its two-dimensional event horizon surface. If this is true, then light falling into a black hole might not actually travel to the interior at all. Instead, it might be immediately encoded as information on the horizon, with the apparent three-dimensional interior being merely a holographic projection of this surface information. This holographic view suggests that the question of whether light slows down or stops inside a black hole might be fundamentally misguided. If the interior is holographic, then light does not have an independent existence within the black hole. The photons we think of as falling toward the singularity might be better understood as excitations of the holographic field that describes the black hole's surface. In this framework, asking about the speed of light inside the black hole would be like asking about the speed of images in a movie. The question assumes a reality that may not actually exist. String theory offers additional possibilities for how light might be trapped within black holes. In string theory, fundamental particles, including photons, are understood as vibrating strings in a higher dimensional space. The extreme curvature inside a black hole might cause these strings to behave in novel ways, potentially becoming trapped in compact extra dimensions that are normally invisible to us. Light falling into a string-theoretic black hole might not disappear, but rather might be redirected into dimensions beyond our normal three-dimensional experience. Some string theory models predict that black holes might be connected to other regions of space-time through structures called wormholes. In these scenarios, light trapped inside a black hole might not be destroyed, but rather transported to another location, possibly even another universe. The light would still be trapped in the sense that it cannot return to its point of origin, but it might continue to exist and propagate in a completely different region of the cosmic landscape. Loop quantum gravity, an alternative approach to unifying quantum mechanics and general relativity, suggests that the classical singularity at the center of a black hole is replaced by a quantum bounce. In this picture, matter and energy falling into a black hole would be compressed to a maximum density and then rebound, potentially emerging from a white hole in another region of space-time. Light trapped in such a black hole would undergo a dramatic transformation during the bounce, but it might ultimately escape into a new region of the universe rather than being permanently destroyed. The concept of black hole complementarity proposes that light can be simultaneously trapped and not trapped, depending on your perspective. From the viewpoint of an outside observer, light falling toward a black hole appears to slow down and become trapped at the event horizon, its information spread out over the horizon's surface through Hawking radiation. From the perspective of someone falling with the light, however, the photons pass smoothly through the event horizon and continue toward the singularity. Both descriptions are supposedly valid, representing different aspects of the same underlying physics. This complementarity principle suggests that the question of whether light is truly trapped might not have a unique answer. The fate of light inside a black hole might depend fundamentally on the reference frame from which you ask the question, revealing the deep observer dependence that characterizes so much of modern physics. This perspective challenges our intuitive notion that physical events should have unique, observer-independent descriptions. Recent developments in quantum information theory have suggested new possibilities for how information might be preserved even when light appears to be trapped inside black holes. Error-correcting codes originally developed for quantum computing might operate in the quantum geometry of space-time itself. Light falling into a black hole might be protected by these natural error correction mechanisms, allowing its information to be recovered even after the black hole evaporates through Hawking radiation. The firewall paradox has forced physicists to reconsider what it means for light to be trapped at the event horizon. If quantum mechanics requires that information be preserved, and if Hawking radiation must be thermal, then some theories predict that the event horizon should be filled with high-energy photons that would destroy any information trying to cross it. In this scenario, light would not be trapped in the sense of being preserved inside the black hole, but rather would be immediately destroyed and its information encoded in the firewall of radiation at the horizon. Alternative theories propose that the firewall paradox can be resolved by modifying our understanding of how space-time behaves near event horizons. Some models suggest that the horizon itself might be a dynamical surface that moves and fluctuates in response to infalling matter and radiation. Light encountering such a dynamic horizon might be trapped in complex ways that allow information to be preserved while respecting the requirements of both quantum mechanics and general relativity. The study of analog black holes in laboratory settings has provided new insights into how waves can become trapped in black hole-like environments. Using fluids, ultra-cold gases, or optical systems, researchers have created analogues of event horizons where sound waves or light waves cannot escape from certain regions. These experiments have shown that wave trapping in such systems can exhibit rich and complex behavior, including the formation of standing wave patterns and the emergence of analog Hawking radiation. While these analog systems cannot fully capture the complexity of real black holes, they suggest that the trapping of waves in curved space-time might be more nuanced than simple classical models predict. The analog studies have revealed that quantum effects can significantly modify how waves behave near horizon-like boundaries, potentially offering clues about how real light might behave inside actual black holes. The concept of black hole mining represents one of the most speculative possibilities for how trapped light might be accessed. Some theoretical models suggest that advanced civilizations might be able to extract energy and information from black holes through various mechanisms, including the Penrose process around rotating black holes, or through controlled interactions with Hawking radiation. If such extraction is possible, it might imply that light trapped inside black holes is not permanently lost, but could potentially be recovered through sufficiently advanced technology. Quantum entanglement between the interior and exterior of black holes raises fascinating questions about the nature of trapped light. If light inside a black hole remains entangled with light that has escaped, then measurements of the external light might provide information about the internal light, even though direct communication is impossible. This quantum connection might represent a form of information transfer that does not violate the cosmic censorship principle while still allowing some access to the information content of trapped light. The many worlds interpretation of quantum mechanics offers yet another perspective on trapped light inside black holes. In this view, every quantum measurement causes the universe to split into multiple branches, each corresponding to a different outcome. Light falling into a black hole might exist in a superposition of being trapped and not trapped, with different branches of the quantum multiverse experiencing different fates for the photons. The question of whether light is truly trapped might then depend on which branch of reality we happen to observe. Recent work on the emergence of space-time from quantum entanglement has suggested that the interior of black holes might not be a fixed geometric structure, but rather an emergent phenomenon that depends on the entanglement patterns between different degrees of freedom. In this picture, trapped light might not exist in a pre-given spatial region, but rather might participate in the very process that creates the illusion of interior space. The light would be trapped not in space, but in the quantum correlations that give rise to the experience of spatial separation. As we explore these various theoretical possibilities, we begin to appreciate just how profound and multifaceted the question of trapped light really is. Each approach offers different insights into the nature of information, space, time, and quantum mechanics in extreme environments. The fate of light inside black holes serves as a window into some of the deepest questions in theoretical physics, touching on issues that go to the heart of how reality is constructed at its most fundamental level. The diversity of theoretical possibilities also highlights how much we still do not know about black holes and the extreme physics they represent. Each model makes different predictions about what happens to trapped light, and future observations and experiments might help us distinguish between these alternatives. Until then, the fate of light inside black holes remains one of the most captivating mysteries in modern science, a puzzle that continues to drive new discoveries about the nature of our universe. Inside a black hole, light may behave differently than we expect. Could it be trapped, stretched, or even altered beyond recognition by the singularity's immense gravity? As we venture deeper into the theoretical landscape surrounding black holes, we encounter one of the most profound questions in modern physics. What exactly happens to light once it crosses the event horizon and becomes trapped within a black hole? This question touches on fundamental issues of information, energy conservation, and the ultimate fate of matter and radiation in the universe. The various theoretical possibilities that physicists have proposed reveal just how strange and counterintuitive the interior of a black hole might truly be. The classical view of general relativity presents a seemingly straightforward answer. Once light crosses the event horizon, it becomes trapped on inexorable geodesics that lead toward the central singularity. In this picture, photons continue to travel at the speed of light along their curved space-time paths. But these paths all converge toward a point of infinite density and curvature. The light would be compressed and concentrated along with all other matter and energy that has ever fallen into the black hole, ultimately reaching a state that defies physical understanding. But this classical picture raises immediate questions about what happens to the information carried by light. Every photon encodes information about its source, its energy, its polarization, and its history. If this information is simply crushed out of existence at the singularity, it would violate one of the most fundamental principles of quantum mechanics, the conservation of information. This tension between general relativity and quantum mechanics has driven decades of theoretical research into alternative possibilities for light's fate inside black holes. One intriguing possibility is that light becomes trapped not at a point singularity, but within a more complex structure that preserves information while preventing escape. Some theories suggest that the extreme curvature near the center of a black hole might create closed, time-like curves, regions where space-time becomes so twisted that past and future become intertwined. In such a scenario, light might become trapped in temporal loops, circling endlessly through time rather than space, never quite reaching a final destination. The concept of quantum entanglement offers another perspective on how light might be trapped inside black holes. When light becomes entangled with other quantum systems, its information becomes distributed across multiple particles or fields. Some theoretical models suggest that light falling into a black hole becomes maximally entangled with the quantum degrees of freedom that exist on the event horizon. In this picture, the light is not destroyed, but rather becomes part of a vast quantum network that encompasses the entire black hole system. The holographic principle presents perhaps the most radical reimagining of what it means for light to be trapped in a black hole. According to this principle, all the information contained within the three-dimensional volume of a black hole can be encoded on its two-dimensional event horizon surface. If this is true, then light falling into a black hole might not actually travel to the interior at all. Instead, it might be immediately encoded as information on the horizon, with the apparent three-dimensional interior being merely a holographic projection of this surface information. This holographic view suggests that the question of whether light slows down or stops inside a black hole might be fundamentally misguided. If the interior is holographic, then light does not have an independent existence within the black hole. The photons we think of as falling toward the singularity might be better understood as excitations of the holographic field that describes the black hole's surface. In this framework, asking about the speed of light inside the black hole would be like asking about the speed of images in a movie. The question assumes a reality that may not actually exist. String theory offers additional possibilities for how light might be trapped within black holes. In string theory, fundamental particles, including photons, are understood as vibrating strings in a higher dimensional space. The extreme curvature inside a black hole might cause these strings to behave in novel ways, potentially becoming trapped in compact extra dimensions that are normally invisible to us. Light falling into a string theoretic black hole might not disappear, but rather might be redirected into dimensions beyond our normal three-dimensional experience. Some string theory models predict that black holes might be connected to other regions of space-time through structures called wormholes. In these scenarios, light trapped inside a black hole might not be destroyed, but rather transported to another location, possibly even another universe. The light would still be trapped in the sense that it cannot return to its point of origin, but it might continue to exist and propagate in a completely different region of the cosmic landscape. Loop quantum gravity, an alternative approach to unifying quantum mechanics and general relativity, suggests that the classical singularity at the center of a black hole is replaced by a quantum bounce. In this picture, matter and energy falling into a black hole would be compressed to a maximum density and then rebound, potentially emerging from a white hole in another region of space-time. Light trapped in such a black hole would undergo a dramatic transformation during the bounce, but it might ultimately escape into a new region of the universe rather than being permanently destroyed. The concept of black hole complementarity proposes that light can be simultaneously trapped and not trapped, depending on your perspective. From the viewpoint of an outside observer, light falling toward a black hole appears to slow down and become trapped at the event horizon, its information spread out over the horizon surface through Hawking radiation. From the perspective of someone falling with the light, however, the photons pass smoothly through the event horizon and continue toward the singularity. Both descriptions are supposedly valid, representing different aspects of the same underlying physics. This complementarity principle suggests that the question of whether light is truly trapped might not have a unique answer. The fate of light inside a black hole might depend fundamentally on the reference frame from which you ask the question, revealing the deep observer dependence that characterizes so much of modern physics. This perspective challenges our intuitive notion that physical events should have unique, observer-independent descriptions. Recent developments in quantum information theory have suggested new possibilities for how information might be preserved even when light appears to be trapped inside black holes. Error-correcting codes, originally developed for quantum computing, might operate in the quantum geometry of space-time itself. Light falling into a black hole might be protected by these natural error correction mechanisms, allowing its information to be recovered, even after the black hole evaporates through Hawking radiation. The firewall paradox has forced physicists to reconsider what it means for light to be trapped at the event horizon. If quantum mechanics requires that information be preserved, and if Hawking radiation must be thermal, then some theories predict that the event horizon should be filled with high-energy photons that would destroy any information trying to cross it. In this scenario, light would not be trapped in the sense of being preserved inside the black hole, but rather would be immediately destroyed, and its information encoded in the firewall of radiation at the horizon. Alternative theories propose that the firewall paradox can be resolved by modifying our understanding of how space-time behaves near event horizons. Some models suggest that the horizon itself might be a dynamical surface that moves and fluctuates in response to infalling matter and radiation. Light encountering such a dynamic horizon might be trapped in complex ways that allow information to be preserved while respecting the requirements of both quantum mechanics and general relativity. The study of analog black holes in laboratory settings has provided new insights into how waves can become trapped in black hole-like environments. Using fluids, ultra-cold gases, or optical systems, researchers have created analogues of event horizons where sound waves or light waves cannot escape from certain regions. These experiments have shown that wave trapping in such systems can exhibit rich and complex behavior, including the formation of standing wave patterns and the emergence of analog Hawking radiation. While these analog systems cannot fully capture the complexity of real black holes, they suggest that the trapping of waves in curved spacetime might be more nuanced than simple classical models predict. The analog studies have revealed that quantum effects can significantly modify how waves behave near horizon-like boundaries, potentially offering clues about how real light might behave inside actual black holes. The concept of black hole mining represents one of the most speculative possibilities for how trapped light might be accessed. Some theoretical models suggest that advanced civilizations might be able to extract energy and information from black holes through various mechanisms, including the Penrose process around rotating black holes, or through controlled interactions with Hawking radiation. If such extraction is possible, it might imply that light trapped inside black holes is not permanently lost, but could potentially be recovered through sufficiently advanced technology. Quantum entanglement between the interior and exterior of black holes raises fascinating questions about the nature of trapped light. If light inside a black hole remains entangled with light that has escaped, then measurements of the external light might provide information about the internal light, even though direct communication is impossible. This quantum connection might represent a form of information transfer that does not violate the cosmic censorship principle, while still allowing some access to the information content of trapped light. The many worlds interpretation of quantum mechanics offers yet another perspective on trapped light inside black holes. In this view, every quantum measurement causes the universe to split into multiple branches, each corresponding to a different outcome. Light falling into a black hole might exist in a superposition of being trapped and not trapped. with different branches of the quantum multiverse experiencing different fates for the photons, the question of whether light is truly trapped might then depend on which branch of reality we happen to observe. Recent work on the emergence of space-time from quantum entanglement has suggested that the interior of black holes might not be a fixed geometric structure, but rather an emergent phenomenon that depends on the entanglement patterns between different degrees of freedom. In this picture, trapped light might not exist in a pre-given spatial region, but rather might participate in the very process that creates the illusion of interior space. The light would be trapped not in space, but in the quantum correlations that give rise to the experience of spatial separation. As we explore these various theoretical possibilities, we begin to appreciate just how profound and multifaceted the question of trapped light really is. Each approach offers different insights into the nature of information, space, time, and quantum mechanics in extreme environments. The fate of light inside black holes serves as a window into some of the deepest questions in theoretical physics, touching on issues that go to the heart of how reality is constructed at its most fundamental level. The diversity of theoretical possibilities also highlights how much we still do not know about black holes and the extreme physics they represent. Each model makes different predictions about what happens to trapped light, and future observations and experiments might help us distinguish between these alternatives. Until then, the fate of light inside black holes remains one of the most captivating mysteries in modern science, a puzzle that continues to drive new discoveries about the nature of our universe. Inside a black hole, light may behave differently than we expect. Could it be trapped, stretched, or even altered beyond recognition by the singularity's immense gravity? As we stand at the threshold of a new era in astronomy and physics, the future of black hole research promises to unlock secrets that have puzzled humanity for generations. The role of light in these investigations will be more crucial than ever, as advancing technologies and theoretical insights converge to offer unprecedented opportunities to probe the most extreme environments in the universe. The question of how light behaves inside black holes may finally find answers through the remarkable tools and techniques that are emerging on the scientific horizon. The Event Horizon Telescope represents just the beginning of a revolution in black hole imaging. This Earth-spanning network of radio telescopes achieved the historic first images of black hole event horizons. But future expansions of this concept will push our observational capabilities far beyond what seemed possible just a few years ago. Plans are already underway to add more telescopes to the network, including space-based observatories that will eliminate the blurring effects of Earth's atmosphere and provide even sharper resolution of black hole environments. Space-based interferometry will allow astronomers to create virtual telescopes with baselines spanning the entire solar system. Such instruments could resolve features around black holes that are currently far too small to observe, potentially allowing us to study the behavior of individual photons as they spiral toward event horizons. These observations might provide direct tests of whether light truly slows down near black holes, or whether quantum effects alter its propagation in ways that current theories predict. The next generation of gravitational wave detectors will complement these electromagnetic observations with unprecedented sensitivity to the ripples in space-time created by black hole mergers. Future detectors like the Laser Interferometer Space Antenna will be able to observe gravitational waves from black hole systems throughout the observable universe, providing information about how space-time itself behaves during the most violent events in cosmic history. The combination of gravitational wave and electromagnetic observations will create a new form of astronomy that can probe black hole interiors in ways that were previously impossible. Advanced computer simulations are beginning to model black hole environments with extraordinary detail, incorporating both the complex physics of matter falling into black holes and the quantum mechanical effects that might alter light's behavior near event horizons. These simulations use supercomputers to solve Einstein's equations, coupled with the equations of quantum field theory, creating virtual laboratories where physicists can test theories about light's fate inside black holes. As computational power continues to grow, these simulations will become increasingly realistic and may reveal unexpected phenomena that occur in extreme gravitational environments. Machine learning and artificial intelligence are already being applied to the analysis of black hole observations, helping astronomers extract subtle signals from noisy data and identify patterns that might otherwise be missed. Future AI systems will be capable of analyzing vast amounts of observational data from multiple telescopes simultaneously, potentially discovering new phenomena related to how light behaves near black holes. These systems might even be able to test theoretical predictions by comparing observations with millions of simulated scenarios, helping to distinguish between different models of black hole physics. Quantum sensors represent another frontier in black hole research. These devices use quantum mechanical effects to achieve measurement sensitivities that approach fundamental physical limits. Future quantum sensors might be sensitive enough to detect individual photons that have been gravitationally lensed by black holes, allowing astronomers to study how light paths are bent by extreme gravity with unprecedented precision. Such measurements could provide direct tests of general relativity in the strong field regime and might reveal deviations that point toward new physics. The development of quantum communication technologies might even allow new types of experiments with black holes. If quantum entanglement can be maintained over astronomical distances, it might be possible to create entangled photon pairs where one photon is sent toward a black hole while the other is kept for measurement. By studying how the entanglement changes as one photon approaches the event horizon, physicists might gain insights into what happens to quantum information near black holes and whether light truly becomes trapped in these extreme environments. Laboratory analogues of black holes will continue to play an important role in understanding light's behavior in extreme gravitational fields. Researchers are developing increasingly sophisticated systems using ultra-cold atomic gases, optical fibers, and fluid dynamics to create analogues of event horizons where light or sound waves cannot escape. These analog systems allow controlled experiments that would be impossible with real black holes, potentially revealing universal principles about how waves behave in curved space-time environments. The study of primordial black holes, if they exist, might provide unique opportunities to observe black hole evaporation in real time. These hypothetical black holes, formed in the early universe, could have masses small enough that their Hawking radiation would be detectable with current or near future instruments. Observing the final moments of a primordial black hole's evaporation would provide direct tests of Hawking's predictions about black hole thermodynamics and might reveal what happens to the information content of trapped light as a black hole disappears. Advances in theoretical physics are opening new avenues for understanding black hole interiors. The development of holographic duality, which relates gravity in the bulk of spacetime to quantum field theory on its boundary, is providing new mathematical tools for studying black hole physics. These techniques might eventually allow physicists to calculate exactly what happens to light inside black holes by studying equivalent quantum field theory problems that are more mathematically tractable. String theory continues to evolve and might eventually provide a complete description of quantum gravity that resolves the paradoxes associated with black hole information. Recent developments in string theory have suggested new mechanisms for information recovery from black holes, including the possibility that black hole interiors are connected to their exteriors through quantum wormholes. These theoretical advances might fundamentally change our understanding of what it means for light to be trapped inside a black hole. The emerging field of quantum gravity phenomenology seeks to identify observable consequences of quantum gravity theories that might be detected with current or near-future experiments. Some proposed effects include modifications to light propagation in strong gravitational fields, subtle violations of Lorentz invariance, or the existence of additional polarization states for gravitational waves. Detecting any of these effects would provide crucial clues about the correct theory of quantum gravity and its implications for light's behavior inside black holes. Multi-messenger astronomy will become increasingly sophisticated as new types of cosmic messengers are discovered and exploited. Beyond electromagnetic radiation and gravitational waves, future astronomers might detect neutrino emissions from black hole environments, cosmic ray signatures of black hole processes, or even hypothetical particles like axions that could escape from black hole interiors. Each new messenger provides an independent probe of black hole physics and might reveal aspects of light's fate that cannot be studied through traditional observations. The development of precision tests of general relativity around black holes will continue to push the boundaries of what we can learn about these extreme objects. Future measurements of stellar orbits around the supermassive black hole at the center of our galaxy will be precise enough to detect subtle relativistic effects that have never been observed before. These measurements might reveal whether general relativity continues to hold in the strongest gravitational fields in the universe, or whether new physics becomes important in these extreme environments. Advances in materials science and nanotechnology might enable the construction of detectors with unprecedented sensitivity to individual photons and their properties. Future instruments might be able to measure not just the intensity and wavelength of light from black hole environments, but also subtle quantum properties like entanglement and coherence that are affected by extreme gravity. Such measurements could provide direct tests of whether quantum mechanics is modified in strong gravitational fields. The possibility of detecting Hawking radiation from stellar mass black holes represents one of the holy grails of black hole physics. While this radiation is predicted to be incredibly faint, future technological advances might make its detection possible. Observing Hawking radiation would provide direct confirmation of one of the most profound predictions of theoretical physics, and would offer insights into how quantum mechanics and gravity interact at fundamental levels. International collaborations are becoming increasingly important in black hole research, as the complexity and scale of modern observations require resources and expertise from around the world. Future black hole observatories will likely be global, or even space-based collaborations that combine the efforts of thousands of scientists and engineers. These large-scale projects will have the resources to tackle the most challenging questions about black hole physics, including the fundamental nature of light's behavior in extreme gravitational environments. The education and training of the next generation of black hole researchers will be crucial for continued progress in the field. Universities and research institutions are developing new curricula that combine advanced mathematics, theoretical physics, observational astronomy, and computational science to prepare students for the interdisciplinary challenges of modern black hole research. These future scientists will bring fresh perspectives and new ideas to the age-old questions about light's fate inside black holes. Public engagement and outreach will continue to play an important role in black hole research, as these mysterious objects capture the imagination of people around the world. The dramatic images of black hole event horizons have already inspired a new generation of students to pursue careers in physics and astronomy. Future discoveries about light's behavior inside black holes will likely generate similar excitement and help maintain public support for fundamental research. The philosophical implications of black hole research will continue to challenge our understanding of reality, information, and the nature of physical existence. Questions about what happens to light inside black holes touch on fundamental issues about the relationship between observer and observed, the nature of information, and the ultimate fate of everything in the universe. These philosophical dimensions ensure that black hole research will remain relevant, not just to physicists, but to anyone interested in understanding our place in the cosmos. As we look toward the future, the study of light's behavior inside black holes stands at the intersection of our most advanced technologies and our deepest theoretical insights. The coming decades promise to bring unprecedented opportunities to probe these cosmic mysteries, and perhaps finally answer the question of whether light can truly slow down or stop in the most extreme environments the universe has to offer. The journey toward understanding these cosmic enigmas will undoubtedly reveal new wonders and deepen our appreciation for the subtle and beautiful ways that light, space, and time interact in the cosmic dance of existence. As we continue to look deeper into black holes, light may offer the key to unlocking some of the greatest mysteries of the universe. Perhaps one day, we will fully understand how light behaves in these cosmic anomalies. Tonight, we have journeyed together through the cosmic landscape of one of the most profound questions in physics. Could light, the fastest thing in the universe, actually slow down or stop when trapped inside a black hole? This question has taken us from the fundamental nature of light itself, through the warped geometry of space-time, to the very limits of human knowledge at the edge of singularities. Along the way, we have discovered that this seemingly simple question touches on some of the deepest mysteries of existence itself. We began our exploration by appreciating light for what it truly is, not just the illumination that allows us to see the world around us, but the fundamental constant that defines the very structure of space and time. Light travels at its unwavering speed of 299,792,458 meters per second, serving as the ultimate speed limit that governs all of reality. This speed is woven into the fabric of the universe so deeply that it determines how space relates to time and sets the boundaries of what is possible in our cosmic neighborhood. Yet even this most fundamental of constants faces its greatest challenge when it encounters a black hole. These cosmic giants represent regions where gravity becomes so intense that it warps space-time beyond our everyday experience. Near a black hole, the familiar concepts of distance and duration become fluid, stretching and compressing in ways that defy intuition. Time slows down, space curves, and the paths that light follows become twisted spirals, leading inexorably toward the center. At the event horizon, that invisible boundary that marks the point of no return, we encountered one of the most profound paradoxes in physics. From the outside looking in, light appears to slow down and freeze at this boundary, never quite crossing over in any finite amount of time. Yet from the perspective of someone falling with the light, the journey continues smoothly inward, with no special significance to the moment of crossing the horizon. This duality of perspectives reveals that the question of light speed is not just about physics, but about the fundamental nature of observation and reality itself. Beyond the event horizon, in the mysterious interior of a black hole, we found ourselves in a realm where our current understanding of physics reaches its limits. Here, the classical description of light traveling along geodesics through curved space-time gives way to quantum mysteries and mathematical infinities. The singularity at the center represents not just a point of infinite density, but a boundary of human knowledge, a place where our theories break down and point toward new physics yet to be discovered. Through our exploration of quantum mechanics, we discovered that light might not be the simple, classical phenomenon we often imagine it to be. At its deepest level, light consists of quantum particles called photons that exhibit wave-particle duality, uncertainty principles, and entanglement effects that could fundamentally alter how we understand light's behavior in extreme environments. Near the singularity of a black hole, these quantum effects might become dominant, potentially preventing the infinite compression that classical physics predicts and creating entirely new phenomena that we are only beginning to imagine. The holographic principle opened our minds to the possibility that the interior of a black hole might not be a separate three-dimensional space at all, but rather a holographic projection from information encoded on the two-dimensional event horizon. If this radical idea is correct, then light falling into a black hole might not actually travel to the center, but instead might be immediately encoded as quantum information on the horizon's surface. This would mean that asking about light speed inside a black hole is like asking about the speed of images in a hologram, a question that assumes a reality that may not actually exist. Our investigation of how astronomers study black holes revealed the beautiful irony that these invisible objects reveal themselves through the very light they seem to devour. The brilliant accretion disks that surround black holes, heated to millions of degrees by gravitational compression, create some of the most luminous objects in the universe. Through careful study of this light, astronomers have been able to probe the immediate vicinity of event horizons and test our understanding of how extreme gravity affects the propagation of electromagnetic radiation. The first direct images of black hole event horizons captured by the Event Horizon Telescope marked a historic moment in our understanding of these cosmic giants. These images showed the dark shadow of the event horizon surrounded by the brilliant glow of superheated matter, confirming decades of theoretical predictions and providing visual proof that these exotic objects truly exist. Yet even these remarkable images only show us the boundary of the unknown, the edge beyond which our direct observations cannot penetrate. As we explored the various theoretical possibilities for what happens to light inside black holes, we encountered ideas that stretch the imagination and challenge our fundamental assumptions about reality. From quantum tunneling effects that might allow information to escape from black holes, to string theory models that suggest light might be redirected into extra dimensions, to loop quantum gravity scenarios where the singularity is replaced by a quantum bounce that could transport light to other regions of space-time. Each possibility offers a different vision of light's ultimate fate. The future of black hole research promises even more remarkable discoveries. Advanced space-based telescopes will provide unprecedented views of black hole environments, while quantum sensors will push measurement precision to fundamental limits. Computer simulations will model black hole interiors with increasing sophistication, and laboratory analogues will allow controlled experiments with black hole-like conditions. Machine learning algorithms will sift through vast amounts of data to uncover subtle patterns that might reveal new aspects of black hole physics. Perhaps most intriguingly, the development of quantum technologies might allow entirely new types of experiments with black holes. Quantum entanglement between photons near black holes and distant measurement devices could provide new ways to probe the information content of these systems without violating the cosmic censorship that hides their interiors from direct view. Such experiments might finally resolve the information paradox and tell us whether the information carried by light is truly destroyed when it falls into a black hole, or whether it is preserved in more subtle ways. Yet even as our technologies advance and our theories become more sophisticated, black holes continue to humble us with their mysteries. They force us to confront the limits of human knowledge and to acknowledge that the universe contains phenomena that may forever remain beyond our complete understanding. This is not a failure of science, but rather a recognition of the infinite depth and complexity of the cosmos we inhabit. The question of whether light slows down inside black holes has led us on a journey through some of the most profound concepts in modern physics. We have explored the nature of space and time, the quantum mechanical foundations of reality, the holographic structure of information, and the ultimate limits of physical law. Along the way, we have discovered that this seemingly simple question about light's behavior is intimately connected to the deepest puzzles about the nature of existence itself. As you settle into rest tonight, let your mind wander among the stars and contemplate the cosmic dance between light and gravity that plays out in the most extreme environments the universe has to offer. Picture photons that have traveled for billions of years across the cosmos, carrying information from distant galaxies, only to encounter black holes that bend their paths and challenge their very existence. Imagine the quantum fluctuations that might occur near event horizons, the holographic encoding of information on horizon surfaces, and the possibility that space-time itself might be woven from quantum entanglement in ways we are only beginning to understand. The story of light inside black holes is ultimately the story of our quest to understand the fundamental nature of reality. It is a tale of human curiosity pushing against the boundaries of the known, of mathematical beauty revealing cosmic truths, and of technologies that allow us to probe the most extreme corners of existence. This story is far from over, and future generations will undoubtedly uncover new chapters that we cannot yet imagine. Black holes serve as cosmic laboratories where the laws of physics are tested under the most extreme conditions possible. They are places where quantum mechanics meets general relativity, where information theory intersects with thermodynamics, and where the familiar concepts of space and time are stretched beyond recognition. The behavior of light in these environments provides a window into the deepest structures of reality and may ultimately reveal new laws of physics that govern the universe at its most fundamental level. As we close our journey tonight, we are left not with definitive answers, but with a deeper appreciation for the questions themselves. The mystery of light's behavior inside black holes reflects the broader mystery of existence, reminding us that we live in a universe far stranger and more wonderful than our everyday experience might suggest. Each photon that disappears behind an event horizon carries with it not just energy and information, but also our hopes and curiosities about what lies beyond the edge of the knowable world. Rest now, knowing that somewhere in the cosmos, light continues its eternal dance with gravity in ways that we are still learning to understand. The universe keeps its secrets well, but with each passing year, our growing knowledge brings us closer to comprehending the cosmic choreography that governs the behavior of light in the most extreme environments nature can create. Sweet dreams, and may your rest be filled with the gentle wonder of cosmic mysteries yet to be solved.